We have a lot of great talks planned for today, and we have 2 sessions with a 15-minute break in between. So there are a few things I want to say before we start. First, everybody, please keep yourselves muted at all times during the talk. And at the end of each talk, we have a 5-minute time for question and answers. And for questions, please either write it in the chat or on the Slack channel, or raise your hand and I'll ask you to unmute and ask the question. The speakers, please keep to the time so we can finish on time. And I will give a 3-minute warning by unmuting and saying 3 minutes. And then if you overrun your 10-minute time, I will stop you at 15 minutes and then there won't be any time for questions. So it's best to keep your talks short so we can have a nice discussion afterwards. I mean, even if that happens, I mean, we can obviously there is still the Slack channel and people can continue the discussion there. So I think that's all I wanted to say. Are there any questions, comments? Cool. Okay, so if there isn't much more, then we can start. The first speaker is Ignas Snelle from Leiden, giving us some recent highlights on Nova Network 2. Ignas, please go ahead.
Thank you. Let me see, I have to share my screen. I just told you that I was able to do that. Yes. Can you all see this?
Yes, perfect.
All right. Hello. It's very nice that you're all listening in. My name is Ignas, and the NAC organizer asked me to give a short overview of Nova Network 2 on the formation and evolution of stars and planetary systems, focusing on the key scientific questions of the research, some recent highlights, and future directions. Note that this is very similar to the presentation Inga and I gave to the NOVA Visiting Committee a few months ago. Now, we live in very exciting times. Protoplanetary disks from which planets and possibly their moons are formed can be studied in detail. Exoplanets are found in their thousands, for which the chemical buildup is being deciphered. The most massive stars, which produce the bulk of the chemical elements in the universe, can be studied now in a wide range of environments, but also increasingly complex molecules are found in space with their chemical formation processes being simulated in state-of-the-art astrochemical laboratories. Now, these exciting developments are all in the heart of Network 2. We're clustered around 4 overlapping themes: that of massive stars. This theme has important links with the other networks 1 and 3, planet formation in disks, extrasolar planets, and the molecular universe. Now, massive stars play a key role in the evolution of star clusters and galaxies, but their important formation and evolution is yet not well understood. The bulk of the chemical elements are made and released in the medium through powerful winds, but also by core collapse supernovae and gamma ray bursts. And with the ionizing flux, they form powerful feedback mechanisms affecting star-forming regions. Now, because they live so short but extremely bright lives, massive stars are also the way to learn about star formation processes on cosmic scales. The first stars formed in the universe are thought to have been very massive and also form the progenitors of neutron stars and black holes, whose mergers are now being detected with gravitational waves. One of the long-term goals is therefore really also to understand the formation of the first stars in the primordial universe, which is linked to the populations in low metallicity environments. Just as an example, very interesting recent highlight: 30 Doradus cluster in the LMC was probed using flames on the VLT to measure the star formation history and initial mass function of this cluster, to find that the main episode of star formation started about 8 million years ago, and that about a third more stars above 30 solar masses were formed than predicted by the standard salpeter IMF. And this result actually directly affects the black hole formation rate and the expected rate of mergers detectable through gravitational wave signals. Just very briefly here, because I don't have much time, some more recent wide range results on the left on the formation of close massive binaries by Ramirez Tanis earlier this year. In the middle, a result by Zapartas on supernova type 2 progenitors, showing that 1/3 to half of them have a history of mass exchange. And on the right by Renzo et al. Showing that the 30 Doradus cluster in the LMC is actually ejecting a 150 solar mass star. The future direction of these research are logically really focused on characterizing and understanding massive star populations in very different galactic environments. This is spurred on by and closely linked to the NOVA instrumentation program, moving from multi-object spectrographs on the VLT and William Herschel, such as WEAVE, to the suite of instruments on the ELT, pushing this field really to the most extreme metal-poor galaxies. Now, with the ELT, we can do that up to distances to the Virgo cluster. Network 2 has, of course, a long history of leading research on planet-forming disks. The advent of ALMA and also SPHERE on the VLT allowed us to zoom into the details of planet formation processes with unprecedented sensitivity, pushing the data analysis to actually measure the first protoplanets in a disk. We also combined large surveys to quantify how disk masses evolve during the planet forming era, and we use all that knowledge to shape planet formation theories. What drives our efforts is to understand when and how planets are formed in disks. And of course, connecting to the exoplanet theme, we want to understand how the disk structure and composition affects the diversity and architectures of planetary systems. Again, I just want to highlight here a few exciting results from VLT instruments, Matisse and SPHERE. Matisse is zooming into the inner 1 astronomical unit around young stars and is then able to actually trace the orbital evolution inside the region where rocky planets are forming. With this instrument, Varga et al. Measured a rotating asymmetry in a disk around HD 163296. It is possibly a vortex in which solids can be concentrated, making it a plausible site of current and future planet formation. With the SPHERE instrument, Muro Arena et al. Measured a prominent shadow in the disk around HD 139614. These shadows stretch over more than 180 degrees, and with detailed 3D radiative transfer modeling, they show that this requires a combination of two misaligned regions in the disk, possibly only inclined by a few degrees with respect to each other. Such a misalignment could be caused by a planetary mass companion on an actual inclined orbit. Pushing on further to understand satellite formation around gas giants, Rapp et al. Showed that deep ALMA integration can reveal the gas kinematics of circumplanetary material around wide orbit planets. And this could actually be used to estimate then the companion's mass and to actually distinguish planets from brown dwarfs, as you can see here in the lower part of this slide. Combining now the results from many ALMA and VLA surveys of young systems, Koniec et al. Showed that exoplanet cores must be built early in the embedded phase of star and disk formation. The mass contained in more mature disks and ages of 1 to a few million years is just too small to explain the population of observed exoplanets.
3 minutes.
I have to go faster. Planet formation requires very small grains and pebbles to grow into planetary cores. This bridges very different physical growth regimes and then requires nested codes to run end-to-end simulations. And with this approach, Schoenberg et al. Found that the formation of the TRAPPIST-1 system might in fact feature two different modes of planet formation, planetesimal accretion and pebble accretion. Our future for understanding planet formation is very exciting. With NOVA, we position ourselves in leading roles for key instrumentation to characterize the gas, solids, and ice in disks. And this data enables us then to link the exodiversity of disk of that to the exoplanet population. Now, with the spatial resolution of ALMA and the VLT instruments, SPHERE and ExoMetis, we can identify the states of planet formation in disks and characterize the population of protoplanets formed here. JWST, on the other hand, will give us unique insights into the chemical diversity of the inner disks where rocky planets are forming. And in the second half of this decade, METIS will offer imaging of gas phase lines and thermal emission from hot dust at the resolution of an astronomical unit. Okay, going a bit faster. Yeah, the exoplanet theme is of course close to my heart. We have been part of an ongoing revolution that started in the 1990s. And that is not going to end sometime soon. It's really amazing what has been achieved so far, learning about the enormous complexity and diversity of exoplanets, far beyond what we could have imagined in the solar system. There are many recent actual results we can show here, but let me highlight just two. On the left here is an example of what you can now do with larger samples of planet atmospheric measurements. These are all from Spitzer. And what is shown is that for hot Jupiters below 1700 Kelvin, the day-side flux seem to follow a black body, but that they start to deviate at high temperature, and that this can actually be explained by invoking the onset of inversion layers. And on the right, another very exciting new direction of exoplanets, work about mysterious low frequency, high circular polarized and variable radio emission from nearby M dwarfs. Works done by LOFAR. I would say watch the space, because these radio emissions could well be due to planet-star interactions. The road ahead in exoplanet fields is very clear. In the end, we want to study Earth-like planets, but of course, there are many challenges. And a key NOVA instrumentation like METIS will actually work on these challenges from both sides, from both the transit side and the direct imaging side. Now, both studying disks and exoplanets are very closely tied to questions we are addressing in the context of the exomolecular universe. Our successful approach is here to very closely combine laboratory experiments with observations and astrochemical modeling. With NOVA funding, we have developed unique experimental setups to study the formation of ices and surface reactions leading to increasingly molecular complexity. And our key interest here lies in deciphering how molecules can trace the physics and kinematics in space. And in the larger context, we aim to understand the history of molecules in space and how do we go from molecular clouds to pre-stellar cores and eventually planetary systems. Again, many exciting results could be shown here from the past years, but let me focus on a very recent one here with the Surface-Side 2 experiment. Iopolo et al. Could show that the most simple amino acid, glycine, can form in water-rich ices without the need for energetic radiation, and that those dense and dark conditions are readily found, for example, in pre-stellar cores. Now, this actually provides a crucial pathway that can point to a cosmic origin of amino acids. To position ourselves in a leading role to exploitation of JWST data, the Leiden laboratory has launched a long-term effort to characterize near and mid-infrared spectra of ices, and this data is made available through the Leiden laboratory ICE database. Now, the future of this research team looks very bright with ALMA and the launch of JWST later this year. We will move studying the chemical complexity in single sources to large samples. And our leading role in the ERS ice age with JWST will enable us to build a consistent picture of how ices evolved to cold clouds, to protoplanetary disks, and even further. Let me very quickly now, because I run out of time at the end, let's peer a little bit into the further future. There are such exciting times ahead. Thinking about understanding how planets form and finding life. There are many more aspects about this coming from other fields like geology, biology. We have started already to man bridges, for example, with Pepsi and the Dutch Origin Centers. And yeah, our science and instrumentation development go really hand in hand. And of course, I want to mention here METIS, which is the absolute flagship, and we're all very much looking forward to it. Okay, I will end here. Thank you.
Thank you very much. It was very, very nice to see all these developments. So we have, I think, around 2 minutes or so for questions. Are there any questions? from the audience? You can write it in the Slack channel or in the chat, or just raise your hand.
I had to skip over a few things, so if you have questions about that, please.
Wait, so there's nothing in the Slack either. Okay, so yeah, there are no questions. So yeah, Ignace, so I was wondering, so yeah, I don't know, you wanted to say something about the, but you said that you missed something? I don't know.
Yeah, in the end, I wanted to say something about the high contrast imaging roadmap. Let me see. Yeah, that the future of the high contrast imaging branch really heavily relies on the exotechnical developments here, and that we have clear pathways from a possible upgrade to sphere to an optical extreme adaptive optics instrument for the ELT, and from the other hand in space with the coronagraphic imaging on the Roman Space Telescope towards a more distant future with possible Habex or Louvre type missions, and that the instrumentation group in Leiden is really specialized in this, like focal plane wavefront sensing, liquid crystal coronagraphy, spectral polarimetry.
Cool.
That was all.
Yeah, that's great. So we also have a question from Veronica. Do you want to unmute yourself and ask the question, or should I?
Sure. I just wanted to ask, I'm quite interested in the formation of prebiotic molecules. I wanted to ask what the ice composition was for making that glycine, if you know.
Let me go back to can I go back to these? So this is the work by Iopolo, and I really do hope that one of the co-authors of that paper is actually online and can actually tell you. Let's make this a real workshop.
And there must have been an intermediate molecule as well that I'm also curious about.
Is there anybody online who knows this? I can start guessing and calling out some random molecules, but I don't think that will actually help you.
I'll have to find the paper. It's all right.
Yeah. Sorry about that.
Okay, great. Thank you again for the talk. So I think we need to move on to the next speaker. So we have Mary van de Sande. So first of all, I'm sorry for my bad pronunciation. So yeah,
it's okay.
Please take it away.
Thank you, and thank you to the organizers for giving me the opportunity to talk about dust gas chemistry within AGB outflows. So first of all, the asymptotic giant branch, or AGB phase, is one of the final evolutionary phases in the lives of stars with an initial mass up to 8 solar masses. On the Hertzsprung-Russell diagram, you can find them in the upper right corner. These are red cold stars. The AGB phase is characterized by mass loss. These stars lose their outer layers at a rate between 10 to the minus 8 up to 10 to the minus 4 solar masses per year. And they do so by means of a stellar outflow or a stellar wind. The outflow is thought to be launched by a two-step mechanism, so stellar pulsations facilitate dust formation, which then initiates a dust-driven wind. And thanks to their outflows, AGB stars are important contributors to the chemical enrichment of the interstellar medium, or ISM. About 80% of the gas and 30% of the dust originates from these AGB stars. And their outflows are also very rich astrochemical laboratories. Over 100 molecules and some 15 types of dust, newly formed dust, have been detected so far. And the relevance and importance of AGB stars has been recognized by the ALMA Large Program Atomium. This is the first large program in the field of stellar evolution. And here you can see our postcard from the science paper. So this is a CO emission, around 12 stars in our sample. Red going away from us, blue towards us, green plane of the sky. And it's quite clear that some beautifully complex structures can be present within the outflow, but for the sake of simplicity, we're going to use this schematic. AGB outflows come in two different chemical flavors, carbon-rich and oxygen-rich. And the type of chemistry is determined by the elemental carbon to oxygen ratio of the star itself. If the C/O ratio is larger than 1, there's more carbon than oxygen. We can then assume that most of the oxygen is locked up in the strong carbon monoxide bond, leaving behind only carbon, so carbon-rich chemistry. Similarly, C/O smaller than 1, oxygen-rich chemistry. Chemistry and dynamics are closely coupled throughout the outflow, and we can distinguish three main regions, each characterized by their own chemical and dynamical processes. In the inner ring, close to the star, the chemistry is taken out of equilibrium because of the shocks caused by stellar pulsations. Then a bit further out, dust is able to condense from the gas phase, and it's here that the outflow is launched, the wind is accelerated. And then finally, in the outer region, the material has reached its terminal velocity, and the chemistry in this region is photon-driven. Because of the lower density, interstellar UV radiation can more easily penetrate this region and wreak some havoc. I'd like to point out just the scale of these things. So the outflow goes from the stellar surface all the way to some 20,000 stellar radii. That's about 20,000 AU. These are large stars surrounded by enormous outflows. And within the outflow, there are large gradients in density and temperature. And it's because of these gradients that there is such rich chemistry happening in them. When it comes to chemical models of AGB outflows, we can again divide them into two groups. So either they focus on the non-equilibrium aspect of the chemistry in the inner ring up to the point of dust formation, or they study the gas phase photon-driven chemistry in the outer ring by means of a chemical kinetics model. And together with Catherine Walsh at the University of Leeds, I have included a comprehensive dust-gas chemistry in such a chemical kinetics model. This way, we, for the first time, extend the chemical validity of our model from the outer end into the dust interaction zone. But the main reason why we did that is, of course, that there's observational evidence of such dust-gas interactions, more specifically, depletion of gas phase species onto the dust. Now, the types of chemical reactions that we have included are accretion of gas phase species onto the dust, forming a fissy-sorbed ice mantle. Once on the dust, reactions can still occur, either via a diffusive mechanism or a stick and hit mechanism. And the ice mantle can be destroyed by thermal desorption when the dust is too warm, photodesorption, and mechanical sputtering. The main assumption of our model is that the dust is already present. We're not making any dust, it's already there, and it has a certain grain size distribution. For that, we chose the canonical MRN distribution. Now for some results. Here you can see the abundance of water relative to H2 throughout a bunch of oxygen-rich outflows. The columns are for different outflow densities, and the rows are different types of dust grains. The black lines are the result from gas phase chemistry only. Different shades of blue are different dust gas models. We find that the effect of on the gas phase depends on 4 factors. So first of all, the outflow density. As we increase the outflow density, so we move to the left in this figure, there's more collisions between dust and gas, so more accretion onto the dust, which corresponds to depletion from the gas phase. And in fact, we find that depletion only really occurs in these higher density outflows. We don't really see any effect in the lower density outflows. Then the dust temperature also plays a role. As we increase the dust temperature, so we go up in the figure, the thermal desorption rate increases, so less depletion for warmer dust grains. Then the drift velocity between dust and gas also plays a role. If the dust is a bit faster than the gas, then there's more collisions, so more depletion, but it shouldn't be too fast because then the chemical sputtering takes over. There's a bit of a balance. And then finally, the molecule itself plays a role. Water has a very high binding energy. It really likes to stick onto the dust, but other species, such as CO, not as much. So as gas phase species are depleted from the gas phase onto the dust, an ice mantle is formed. And here I show you the number of monolayers of ice on top of the dust grains in the oxygen-rich, carbon-rich outflow. This is a very large density outflow. Different colors are different types of dust. In the oxygen-rich outflow, we can easily achieve more than 100 monolayers of ice stuck onto the dust, whereas for the carbon-rich outflows, it's somewhere between 1 and 10 monolayers. This is partly because there's more water in an oxygen-rich outflow, and water really likes to stick onto the dust, but also because carbon-rich dust is on average a bit warmer than the dust in the oxygen-rich outflow, so more thermal desorption.
3 minutes.
Thank you. Now, these results led to some follow-up questions, namely, how do the ices, and more specifically the composition of the ices, contribute to the interstellar medium? Because interstellar dust grains are thought to have this layered structure of a silicate core surrounded by inner organic mantle and then an outer ice mantle. The inner organic mantle is composed of refractory organic material. It's important to a bunch of its properties. And the refractory organics are thought to be formed by photoprocessing in the diffuse ISM, so photoprocessing of interstellar ices in the diffuse ISM. Then we were wondering that maybe this photoprocessing could already occur in the AGB phase, so in the prenatal phase of interstellar dust grains. To that end, we included the new reaction type photoprocessing of the ice, where complex ices can be turned into refractory organic material. And once that's done, to a species, it's inert and it cannot participate in the chemistry anymore. And we also assume that a complex ice either has 3 or more carbon atoms or 2 carbon atoms and 1 heavy atom, because we had to make decisions. And the reaction rate is estimated from laboratory experiments. So here you can see the number of monolayers of ice, the solid lines, and refractory material, the dashed lines, again for carbon-rich, oxygen-rich outflow. Different colors, different outflow densities. Let's start with the oxygen-rich outflow because that's a bit easier. So there's about 10 monolayers maximum in this higher density outflow. And the number of monolayers increases with increasing outflow density, which doesn't come as a surprise anymore. But as you can see, the amount of refractory material is very limited. So the maximum is 10 to the minus 5 monolayers. So only a 1,000% of the surface is covered. This is because it's an oxygen-rich outflow. There aren't that many carbon-rich ices. Our feedstock is very limited. Oxygen-rich dust is only negligibly covered. The situation is very different for the carbon-rich outflow because there's plenty of carbon-rich dust. Carbon-rich ices. So again, there's less carbon-rich ice, but it's efficiently transformed into refractory material. So almost 10% of the surface is covered. But what is especially interesting is that also these lower density outflows, so the brown and purple lines, are quite efficient in forming refractory material. That's because they are low density, so interstellar UV radiation can penetrate more easily. And what we see here is that almost as soon as a complex ice species is present onto the dust, it gets photoprocessed into a refractory material. To estimate the contribution of AGB stars to the refractory organic material in the ISM, we ran a grid of models based on observations, so mass loss rate versus outflow velocity, color map refractory coverage, and then we also used 3 different sets of parent species. This is for carbon-rich outflows because, well, oxygen-rich outflows didn't produce much. On average, carbon-rich dust has a surface coverage of 3 to 9%. So it's not bare, but it's not a lot. It's not significant enough to influence the ISM. Again, there's this trend with outflow density. So, and the maximum coverage ranges from 8 to 22%. So that's quite interesting. But in order to have a better estimation of the contribution of AGB stars to the ISM, we need to have a better grasp on various parameters, such as the drift velocity between dust and gas, as well as binding energies and reaction rates. To conclude, AGB outflows are interesting astrochemical laboratories. We have developed a novel dust gas chemical model and found that gas phase species are readily depleted in high density outflows. This leads to the formation of an ice mantle, but photoprocessing of this ice mantle leads to some refractory coverage in carbon-rich outflows, but it's too low on average to significantly influence the ISM. So we need a better grasp, but well, in order to have a better estimate, we need a better grasp on various parameters. Thank you for your attention.
Great, thank you very much. So I think we already have a question. So Frank, do you mind unmuting and asking the question, or do you want me to ask it?
Sure, I can ask a question. I was wondering, a long time ago, I worked a bit on modeling. I was wondering whether your model is completely spherically symmetric, or whether it at least allows for some smaller scale asymmetries, clumpiness in the material.
No, the results that I showed you so far are all spherically symmetric, but we have the possibility of including clumpiness via the porosity formalism. But I haven't combined both models yet, but there's definitely the possibility to do so.
Great, thank you.
And so, are there any other questions? Is there anything in Slack?
No, nothing on Slack yet.
So I also was wondering about the dust distribution. What dust distribution do you use in your models? So what is the maybe maximum grain size or something?
So we use the canonical MRN distribution, and now of course the minimum and maximum grain sizes elude me, but it's predominantly smaller grains in these outflows. But we can also actually tweak the grain size distribution, and that's another one of our papers. It's a 2020 paper. We've been having some fun with this model because the grain size distribution does influence the effect of dust gas chemistry on both the gas phase and whatever is stuck onto the dust. So.
Oh, perfect. Thank you. Let's see. Are there any other questions? Anybody?
Stop sharing.
Oh yeah, we've got. So Paul, do you mind unmuting?
Yes, I have another asymmetry question. I suppose you assume that the dust is symmetrically built up, but I suppose that if it develops some asymmetry, it might just keep that very well in the outflow. And that might give you some polarization effects. And is there evidence for that? Or
for polarization of dust around AGB stars? Yes, there's been observations using the sphere Zimpole instrument of the VLTI. But one way to, the dust is more of an abstract concept in this model. It's not actually there. But one way to include such, like for example, porous grains is to increase the number of binding sites, because in a porous grain, well, there's more surface than on a spherically symmetric, but the effects it can have on polarization is something I have not yet looked into, but I'll keep it in mind. Thank you.
Yeah, I was also thinking when it sees the radiation field from one side, probably being stronger, and so that is a built-in asymmetry in it, unless it just keeps turning around.
Yes.
It's I don't know if you'll ever get this answer.
I think a Vietnamese group has been working on that. In fact, I'll take a look at some papers and post them on Slack for you if I find them.
Thank you.
Great. Okay, so I think in the interest of time, we can move on to the next person. Thank you very much again for the very nice talk. So next we have Anna Monreal-Ibero from Leiden, talking about the atmosphere, talking about galactic planetary nebula with MUSE. So please start. Yeah.
So can you see my presentation?
Yes. Yeah, perfect.
Okay, my name is Anna Monreal-Ibero. I'm coming from Leiden. And first of all, I wanted to thank the organizers for having scheduled this presentation. I am new or almost new here in the Netherlands, so this is the way for me to introduce to this community. What I am going to discuss is how integral field spectrographs in general, and MUSE in particular, can help us to gain knowledge on planetary nebulae and better understand this kind of objects. This is a work that I am doing together with Jeremy Walls at ISO. And the results that you will see through the presentation to support or to illustrate this statement has been extracted from these 3 papers here that we have published in astronomy and astrophysics. So, but first of all, why do we want to study planetary nebulae? So I thought about several interested parties. The first one, you know that planetary nebulae are the corpse that the star, low mass star leaves when it dies. So in that sense, studying this kind of objects is like a tool to understand how is the evolution of these stars while they are in the HEV phase. It will be like doing the autopsy of the stars that we have seen in the previous presentation. Another interested party are those researchers that are interested in interstellar medium, and for them planetary nebulae will be tracers of the chemical content of this interstellar medium, and also they are very good laboratories where we can study interstellar medium with very large range of physical properties. You have regions with high and low ionization, you have compact density nodes, you have the halos that has very low density, and you have material covering a wide range in temperatures, okay? And the last interested party that I had identified as those astronomers that are interested in galaxies themselves. And for them, planetary nebulae are a tool to know about the distance to the galaxy and also to learn about the stellar populations of the galaxy where they are finding these planetary nebulae, and also to as traces of the dynamics of the galaxy. And this is a selection of pretty pictures of with the HST of several planetary nebulae. And we see that they display a variety in terms of morphology. There are some that are, I would say, even boring, like this one, IC418. There are others that present bipolar morphology, like, for example, this two or this one. There are others that present low-scale structure, like this one that has these radial fingers, or this one here with these knots. And this complexity that here we perceive as a morphological complexity is a reflection of a complexity at the level, at the structural level and the physical and chemical properties of the nebula itself. And to grasp this complexity, one would like to have 2D spectroscopic information all over the face of the nebula, to learn about these physical and chemical properties. And this is where integral field spectroscopy comes to the rescue. However, this is not a new technology, but if you look in the literature about works that make use of this technique to study planetary nebulae, there are not that many. And this is because IFUs that we had so far had a field of view that was relatively small compared to the size of galactic planetary nebulae. So if you wanted to cover the whole face of the nebula, you needed to do a mosaic with many tiles, and that was expensive in terms of exposure time. But now with MUSE, well, this is doable. Many galactic planetary nebulae fits within the field of view of MUSE. And when you need to do a mosaic, usually with a few tiles, is enough. So let's illustrate a bit what kind of results you can obtain for planetary nebulae with the two PN that we have observed so far, NGC 7009 and NGC 3132. The first one, NGC 7009, was observed during the science verification of MUSE, and it fits very nicely in one pointing with the instrument. These two images are not at scale, so this one on the right is actually larger on the sky, and it was needed minimum 2 pointings, but actually it was done with 3 pointings to cover the whole face of the nebula, and this one was observed during the commissioning of the instrument. The first thing that you can look at is how is the extinction. And in both nebula, we found evidences of a small and large scale dust structure within the nebula. You see that extinction is higher in the ring in both of them. Here is very clear, and it is especially high in this part of the ring of NGC 3132. Then you can also look at the physical properties. And within the spectral range covered by MUSE, you have actually several diagnostics that can be used to trace the electron temperature. So when you map all these temperatures by means of these different diagnostics, we found, independently of the diagnostics, large spatial variations within the planetary nebulae for both of them. And also we found that temperatures derived when using collisionally excited lines were always higher than when using recombination lines or the passing jump. For the electron temperature, there are not that many diagnostics, but well, there are a couple. And again, for both of them, we found large spatial variations within the nebula itself. But here, the behavior was different depending on the nebula that you were looking at. For NGC 7009, we were getting high densities in the inner part of the nebula, while for NGC 3132, the densities were higher in the rim. Yeah.
3 minutes.
I'm going to discuss a bit about abundances. I will say there is a respectable number of ions that you can trace with MUSE, and also some total abundances, not many. Here I'm going to discuss oxygen, and only for the case for GC 3132, but the result that the conclusion was the same for the other nebula. So in the upper row, I have put the ionic abundances for the 3 ions that are available within the MUSE spectral range. This is neutral oxygen, this is single ionized oxygen, and this is 2 times ionized oxygen. And if you see the row as a whole, I think this is a beautiful way of displaying the ionization structure within the nebula. In the inner parts, we have high abundance in 2 times ionized oxygen, while we have low abundance for single ionized oxygen and even lower for neutral oxygen. And then the situation is reversed when you go to the outer part of the nebula. Then to calculate the total abundance, the standard, the usual way, is adding the abundances that you are able to see with the information that you have at hand, and then include a correction factor that takes into account those ions that you are not able to see. We call these factors ionization correction factors in a display of originality. And determining the proper ionization, or the best ionization correction factor for each situation, is a line of research by itself. And in that sense, MUSE can provide constraints that help us to decide how good or bad different proposals for ionization correction factors are. And this is illustrated in the lower row, where we have derived the total abundances for oxygen using 3 different proposals. And our expectations from the way stars evolve in the latest stage of their life is that these maps should be flat. And we see that none of the 3 is fully, completely flat, but the best proposal that has been done so far is this one, the ionization correction factor proposed by Torres and Painberg and Painberg. I'm going to finish by discussing a bit about kinematics, because when you compare the expansion velocities of planetary nebulae and the spectral resolution of MUSE, one might think that MUSE does not have much to say because the spectral resolution is relatively moderate. And here I think I'm going to put an example where MUSE has actually something to say and something to contribute. This is the nebula, NGC 3132. This is the part that you have already seen so far. And beside that, we have detected these 2 low surface brightness towards the north and the south of the nebula in nitrogen 2. And with the information that was known from this nebula, before this data, the best explanation for the intrinsic structure of this nebula that we have so far was not an elliptical nebula, but something like a diabolo that is orientated in this direction. These 2 circles represent the 2 sides of the diabolo. So with MUSE, we can derive the velocity field for the nebula by means of different emission lines. Here I put H alpha on the right and O1 on the left. H alpha comes, let's say, along the whole ionized nebula along the line of sight, while O1 comes from the most external layers of the nebula. And we see that the velocity field from O1 is much more structured than the velocity field that you see in H alpha. And this one actually has the shape of two interleaved rings, one with blue velocities and another one with red velocities. And that made us to propose that the orientation of the diabolo was not actually as it is suggested here, but something like that. And this orientation actually allows to explain much better the low surface brightness structures that we have seen towards the north and the south. This is all that I wanted to discuss. The main takeaway message from the presentation is not each and every one of the single results that you have seen in the previous slides. You can go to the papers for that and see the details in there. But the more general conclusion that MUSE or MUSE-like observations are extremely useful to study planetary nebulae and offers an opportunity to strengthen and expand the role of planetary nebulae as interstellar medium diagnostic laboratories. And that's all. Thank you for your attention.
Thank you very much for the nice talk. So I think we already have a question from Peter. Do you want to perhaps unmute?
Sure. So your last slide about the kinematics, the red and the blue shift, do you have, because I'm wondering how you computed these velocities, and it's easy to see how well that works if you take these position velocity slices, because you have a data cube, so you can take a slice along a certain position angle and then look at the velocities if they're single or double or triple.
Not me, but there are Fabry-Perot information for certain directions in this nebula. And with Fabry-Perot information, you can see the two components in some places, not everywhere. And when there are two components, you see that the component that is, or that in this sketch that the diabolo is orientated in this way, the component that should be behind is very faint. So with MUSE, you cannot resolve the two components, but you know that the one that is dominating is the one that is closest to you. Yeah. So no, I have not made the cuts, but the cuts exist at higher spectral resolution in the literature. That would be nice.
Okay, thank you.
Cool, thank you very much. So are there any other questions in the Slack channel maybe? No?
No.
No. So I was also wondering myself, so this sort of, I don't know, maybe arms, I don't know, that you see in nitrogen, do you also see it in other molecules or no?
Yes. Actually, when I saw these arms for the
atoms, sorry.
Yeah, I was very happy because nobody has seen these arms. I have discovered something. It seems that they have also been detected in the mid-infrared. Also, we measure the extinction. The extinction here is very high. So because of in the bands in the mid-infrared that were detected, I think there is a lot of molecular gas in here and also in here. Okay. Yeah. And because of the extinction that is high, both together.
Okay, cool. Yeah. No, that makes sense. Yeah, thank you very much. Yeah. So any other questions? I don't see anything. So I guess thank you very much. It was really great. And I think we can move on to the next person. So now we have Nuria Casasayas-Barris from Leiden Observatory talking about the atmosphere of WASP 76b. So yeah, please take it away.
Okay, can you see the screen, right?
Yes.
Okay, perfect. Okay, so good afternoon. My name is Nuria Casasayas-Barris. I am postdoc at Leiden Observatory. And today I'll talk about the atmosphere of WASP 76b seen with CARMENES spectrograph. So first of all, I would like to put in context our planet, which is WASP 76b. And for that, we first need to know that we currently know more than 4,300 exoplanets. And here in this figure, I show all of these exoplanets that have mass measurements. So you see each of these red points is one of these exoplanets. In the vertical axis, you see the mass, and in the horizontal axis, you see the semi-major axis, which is basically the separation between the planet and the star. So you also see here some planets of the solar system as reference. So in the red points, you can clearly observe different samples of planets, and the one that we are interested in here are the hot Jupiters. Hot Jupiters are exoplanets that have masses similar to Jupiter and Saturn, but they are really close to their host stars. So we see that the separations are around 0.04 or 5 astronomical units. So this makes their temperature increase, and their temperature, their characteristic temperature around 1000 Kelvin or even higher. So if we focus on this sample of exoplanets, and there is another subsample inside, which are called the ultra-hot Jupiters, which are exoplanets with temperatures higher than 2000 Kelvin. Currently, we know around 40 of these ultra-hot Jupiters, and these are the ones that I show here in this figure. We see their temperature and also their density. And among these planets, we can see our target, which is WASP-76b. So WASP-76b is an ultra-hot Jupiter. It has a temperature of around 2200 Kelvin. It's a quite big planet with a radius of 1.8 Jupiter radius and a mass below 1 Jupiter masses. And it completes an orbit around the star with only 1.8 days. So it's really close to its host. You see here the separation. And also this planet is orbiting on a star, which is quite bright. So all these characteristics make WASP-76b a good target for transmission spectroscopy studies. Also, we need to know that for this planet, we expect quite extended atmosphere. So what about ultra-hot Jupiters? So ultra-hot Jupiters are these planets which are really close to their host, so they receive a large amount of irradiation. So, and they are also tidally locked, which means that they always have one side of the atmosphere facing the star and the other that it's not. This produces that what we call a permanent day side and a permanent night side. So if we focus on the day side, the temperature here can reach temperatures higher than 3000 Kelvin. So we expect this side to be cloud-free. And also due to the high temperatures, the molecules cannot survive, so they are thermally dissociated and the atoms are ionized. If we focus on the night side, the temperatures can be lower than 2000 Kelvin. Then here we can find clouds, the molecules can form, and also the atoms can be in their neutral forms. So we see that they clearly have two very different sides of the atmosphere. So here we use transmission spectroscopy to study the atmosphere of WASP-76b, and we use high spectral resolution observations. Transmission spectroscopy means that we need transiting planets, so we can monitor the star when the planet is and when it's not transiting. This means that we have observations when the planet is before and after the transit and during the transit. When we are observing before the transit, we are only receiving the stellar light. So if we imagine that we receive one spectrum, this would be one spectral feature from the star. So we don't receive anything from the planet now. When the planet starts transiting, part of the stellar light goes through the atmosphere of the exoplanet, and depending on its composition, part of this light, this stellar light, is absorbed. So it creates some spectral features, some extra absorptions in our observations. These are the ones that we are trying to measure. And after the transit, we observe again only the contribution from the star. So if we compare the data obtained when the planet is and when it's not transiting, we can somehow isolate these extra features from the planet. And this is what we observe here. So what we are trying to do is measuring some features which have this shape. So before and after the transit, we don't see anything. But during the transit, we see that there is these extra features appearing, which are the absorption from the exoplanet. And also you see that they are shifting, they are changing their velocity during the transit. And this is because at high resolution, we are able to measure the change in radial velocity of the planet, because during the transit, first is moving towards us in the first half of the transit, and then it's moving away from us. So this radial velocity change produced that the spectral features from the planet that we want to measure are changing their position in time. So we need to remember this figure because this is what we are trying to measure here. So here we have CARMENES observations, but we need to know that WASP-76b has already been observed with other facilities, with HARPS, for example, and with ESPRESSO. HARPS is in a 3.5 meter telescope, while ESPRESSO is in an 8-meter telescope. So you can imagine, well, what do we want to do now with CARMENES, which is in a 3.5 meter telescope, so it's smaller than the VLT. But well, if we focus on the wavelength region covered by these spectrographs, we see that HARPS and ESPRESSO cover mainly the optical region. And with these observations, there's been detections of ionized calcium, iron, sodium, alpha, and potassium in the atmosphere of this planet. But CARMENES covers this region here, so it's redder wavelength. In this region, we can find species like the ionized calcium triplet or the helium lines. So these are the kind of lines or species that we are trying to measure here, and which have been already found in other exoplanets. So first we focus on the calcium triplet lines, and here you see the results. These are the results. Each column is the results from one of these lines of the triplet. And here you need to remember now this figure that I was saying before, that it seems like here you see it, the figure in small. So yeah, so you see here that for the first and the last lines, we don't see any absorption. This is mainly because the lines are faint, so they are in the noise. But for the intermediate line, which is the strongest, you will see something red here, and this is the absorption from the exoplanet, that it's moving from here to here. And this is what tells us that there is something happening. And if we combine all these features, we get the transmission spectrum, which is the second row, where we clearly detect the calcium in the atmosphere of this planet. Focusing on this spectral line, we can compare with models, this line, which models are computed assuming different temperatures and rotational broadenings. And we can, although the signal to noise is low, we can say that to explain this profile, we need some kind of broadening mechanism, which could be winds or the tidally locked rotation of the planet plus another thing. And also that to explain the depth of the lines, we need temperatures higher than the equilibrium, which is something expected. And then for this, well, these calcium lines have been found in other ultra-hot Jupiters. And also for this same planet has been found the ionized calcium, but using the Agenken lines. So this is something, this detection is something consistent. And also for this kind of exoplanets at these extreme temperatures, the calcium ions are expected to be more numerous than their neutral form. Now we look for the helium. The helium lines are interesting because the helium lines triplet at 1083 nanometers are interesting because they are tracers of extended atmospheres and evaporation. And this is because they are created under intense X-rays and extreme ultraviolet irradiation. So if we have an exoplanet which receives this kind of irradiation, this irradiation hits the gas and produces a radiative ionization of helium, which increases, which makes an expansion, which produces an expansion of this atmosphere and can produce mass loss. So if we study these lines in the transmission spectrum of an exoplanet, we can study this phenomena. And here you see the results that we obtain for the helium line. As you can see, they are really noisy and the absorption is quite faint. This is because mainly the signal to noise of the data is low, but also there are some residuals that fall close to our lines, our helium lines. And these residuals are due to the Earth contamination. So that we have some lines from the Earth atmosphere that are contaminating probably these results. And for this reason, we can only take this result as an upper limit, and we get a 0.9% absorption upper limit. Then in order to know if a planet like WASP-76 could have helium actually in its atmosphere, we decided to measure the XUV flux that this exoplanet receives. And for that, this is the value that we obtain. You again see that it's only an upper limit. And this is because the star is quite far from us, and it's at 195 parsecs. And it also has a really close companion that could be somehow contaminating our measurements. So, well, in any case, with these upper limits, we can put in context our planet in terms of the helium. And here you see all the exoplanets that have helium measurements in the literature in terms of the absorption level and also the XUV flux that they receive. So we see that was 76 falls here. These are all the values that he could get, the real values that we could find for this planet, because this is an upper limit. But although we are not able to conclude if there is helium or not, we are able to say that this could hold, this planet could hold an evaporating helium envelope. And we show that this is a good candidate for further studies of helium, especially using instruments like CRIRES Plus at the VLT. And now I'll finish leaving here the conclusions, and I'll take any questions. Thank you.
Thank you very much. So are there any questions? Oh, yes. So yeah, please, yeah, go on. Yeah. Harry.
Oh, yeah. I didn't know if I was supposed to go. Yeah.
Mm-hmm.
I had a question about the unusually wider width of the calcium line.
Mm-hmm.
Yeah, maybe it's a naive question. Could this be pressure broadening? Because I mean, calcium is very easy to ionize, right? And so maybe it's coming from a very high pressure gas.
Yes, sure.
Pressure broadening be giving you that. And
Yes, it could be. Yeah.
okay.
We were basically studying this kind of like rotational broadening, which is the basic one, and because the signal to noise of the data is not that high, so it was basically, yeah, trying if this needs some kind of broadening mechanism to explain the profile. But yes, it could be pressure broadening. Yeah.
Thanks.
Thank you.
Great. So we also have another question from Jean-Michel. Am I right? Yeah.
That's right. Thank you. Thank you, Nuria, for these very, very nice talks and very nice results. So my question is actually following Ari's questions. When you're looking at the calcium line, ionized calcium, do you have an idea of how extended is the envelope of calcium that you're looking at? And how far from the Roche lobe you are?
No, it's not reaching the Roche lobe. This is, I measured it, but now I don't remember the altitude. I think it was a quite 1.2 radius of the planet or something like that. It was not that high, actually.
Okay, so you're well below. Yeah.
Yes.
Okay.
Yeah.
Very interesting. Thank you.
Thank you.
Oh, well, in that case, I don't know if pressure broadening is reasonable at 1.2 times the planetary radius.
Yeah, indeed.
Cool. So we also have another question from Paul. Do you want to?
Yes. Maybe this is a stupid question, but on Earth, we see the weather getting these weather patterns due to Coriolis forces because the Earth rotates. And you say this thing rotates around the star in about 1.81 days. So it rotates. It must have some Coriolis forces on its atmosphere. So is there some asymmetry that you can detect in your observation?
Yeah, I think this could be something detectable in helium, for example, because you expect it to be in the outer parts of the atmosphere. So probably if the helium was quite strong, this should be something that could be detected actually when looking at the different, so how the absorption evolved in time during the transit. It could probably, we could see this effect actually. But for this planet for which the helium is not that strong, I think it's difficult. But I think for other planets which have shown like a 3% of absorption of helium, this could be something that could happen, yeah.
Probably also depends on the mixing from once it gets out of the hotspot.
Yes.
Well, that's interesting.
Thank you.
Thank you very much. So I think it's in the interest of time, let's move on. And if there are more questions, you can always continue the discussion in the Slack channel. So the next person we have, I think, Sanna Blut from Leiden Observatory. So yeah, please go ahead.
Yes, thank you. My name is Sanna Bloot from the Leiden Observatory. I am currently a master's student, and I am doing my project with Joe Kellingham and Huub Rutgering. And I'm going to talk about APEP today, which is the brightest and most luminous non-thermal colliding wind binary that we've found so far. So before I start talking about APEP, I'll have to give a bit of an introduction. So first I'll start talking about Wolf-Rayet stars. Wolf-Rayet stars are an evolutionary stage in the life of the most massive stars, by which we mean that they have an initial mass of over 25 solar masses. There are different types of these stars that we can distinguish based on their spectrum. So for example, there are WC Wolf-Rayet stars, which have a lot of carbon in their spectrum, and WN Wolf-Rayet stars, which have a lot of nitrogen in their spectrum. This phase of the life of a star lasts about 100,000 years, so compared to its entire lifetime, that is pretty short. And one of the most interesting things about these stars is that they are most likely long gamma ray burst progenitors if they are rapidly rotating. Now, these stars don't always come alone. They are often found in binaries with other massive stars, which actually also makes them possible LIGO source progenitors. Now, in these situations, there's a pretty large mass loss, by which we mean about 10⁻⁴ solar masses per year, and very fast winds on the order of 1,000 kilometers per second. What you see here in the animation is the Wolf-Rayet star in the middle with an O-type star orbiting it. And you can see here, this is the point where the winds collide, at which there's a lot of interesting shock physics happening, and there's a lot of non-thermal emission coming from this particular region. And behind the O star, there's a part that is a lot more calm than the rest. And there is a lot of dust formation happening over there, which we actually see observationally. This is one of the most famous Wolf-Rayet binaries. You can clearly see the tail of dust moving. Now, then I'll move on to APEP. As I've said, APEP is the brightest and most luminous non-thermal colliding wind binary so far. Here on the left, you see the dust plume that is produced by the colliding wind binary. It looks a bit different, but it's definitely recognizable as a dust plume. This system is on a 125-year eccentric orbit found by Hanedal, who determined the orbit based on the spiral patterns. And it consists of 2 Wolf-Rayet stars, which is quite rare. As I've said, the Wolf-Rayet phase of a star is quite short-lived. So to find 2 in one system is not very common. When we measure the wind speed of this system along the line of sight, so the spectroscopic wind speed, we find a wind that is about 3,500 kilometers per second. And in every other system, every other colliding wind binary system that we've seen so far, the dust expansion speed is about the same, which makes sense because for example, if you put a feather in a hurricane, you would not expect the feather to be standing still. You would expect it to be moving with the hurricane. However, this is a weird system. And in this case, the feather is almost standing still. As I've said, we have a spectroscopic wind speed of 3,500 kilometers a second, and the dust is only expanding with about 900 kilometers per second. So in comparison, that is extremely slow. Now, this is not quite determined why this is, but one of the explanations is that one of the Wolf-Rayet stars is rapidly rotating, which would cause it to launch a fast polar wind along the line of sight towards us, and a slow equatorial wind that is driving the dust expansion. And as I've mentioned, a rapidly rotating star, especially a rapidly rotating Wolf-Rayet star, could be a long gamma ray burst progenitor. So that makes this system very interesting. So far, basically everything that I've discussed has been derived from the infrared observations. But as I've mentioned, it is an extremely bright source in radio frequencies. So what can radio observations tell us about this source? First of all, they could provide independent orbit solutions from the infrared data that we have so far, which could confirm the orbit that has been found. And there are a lot of open questions about this source in radio, such as, for example, why it is so bright, because it really is extremely bright. It's over an order of magnitude brighter than most colliding wind binary systems. Furthermore, since this system is pretty unique, it would be somewhat normal to assume that the spectrum might show some unique features as well. And there could be anisotropic winds in this system, as I've said, with the fast polar wind and the slow equatorial wind. And this could change a lot of things because in most systems, there are 2 spherical winds, or at least one from the Wolf-Rayet star. So it would be very interesting to look at that. So we've been doing an observing campaign from 2017 up to now using the Australia Telescope Compact Array. And for some epochs, we even have simultaneous giant meter radio wave telescope. So this is one of the epochs of data that we have. This is actually March from 2019. You can see here in green the compact array data and in blue the GMRT data. The first thing that I want to emphasize again is that this source is really extremely bright. It is about 180 millijanskis over here, whereas most colliding wind binaries are 1 to maybe 10 millijanskis. So this is really over an order of magnitude brighter than most sources. And the second thing here is that there's an extremely steep drop-off in frequency and flux, and these are both in log-log scale. So this is a drop-off from about 160 millijanskis over here at about 0.6 gigahertz to 3 millijanskis over here at 0.25 gigahertz. So this is an extremely steep drop-off, and there are several possible explanations, possible physical effects that could explain this. I don't have time to go into all of them in detail, but the first one is free absorption, which is when a photon is absorbed by the ionized medium along the line of sight. The second is synchrotron self-absorption, when a high energy electron emits a photon and then absorbs it again. And the third is the Rasen effect, which is a plasma effect that also causes an exponential drop-off at low frequencies. And we'd like to thank Benito Marco for helping with the data reduction for the GMRT data. So as I said, there's 3 effects that could cause it, and the most likely one is the free absorption. We have fit all of these models to the data, and the best fit so far is free absorption. You can see here that it can explain the steep drop-off quite well. So if we assume that this is in fact caused by free absorption, we can now start looking at how this would vary along the orbit of the source.
3 minutes.
So for 3 minutes, thank you. So we can now start looking at how this would vary. Williams et al. Made a model for this in 1990, which I'm about to show you, which describes the change in the free absorption along the orbit of a colliding wind binary, as well as the change in the intrinsic flux, because the intrinsic flux depends on the density, which changes as the star moves. So here on the right, you see the frequency on the horizontal axis, flux on the vertical axis again. This is the spectral energy distribution that is predicted by the model. And these 3 frequencies are pinned at the frequencies at which we have the most data. So these will trace out the lie curves over here that we would expect to see. So here we have the time now is about here, and here we have those 3 points again. So as we can see, as it approaches periastron, it drops down as it is mostly obscured. And as it is then somewhere around abastron, somewhere around now, we see very little variation. And then at periastron again, we see very abrupt variation. So we see it again. Here we see very rapid change, and over here at abastron, especially if you look over here, it is pretty much constant. And then it won't change rapidly until it reaches periastron. So here we see that again, but now static. And this is what we would expect in this situation. This is what seems normal. However, when we compare that to our data, we see that the data and the model do not agree. There's quite a significant variability in the data as it moves from about 120 millijanskis in 1994 to about 180 millijanskis in 2017. So that's a variation of 60 millijanskis over 25 years. That is quite a lot. And this model cannot explain it. It obviously does not match. So at this point, we have a few options of what could be causing this. The first one is that possibly the orbital solutions from the infrared are not correct. This is in theory a possibility, as it is possible that the Hanadal paper may have looked at a dust clump and a star instead of 2 stars, but this is somewhat unlikely. But even if we let go of the orbital solutions that we have and just put them as free parameters in the model, we can still not obtain an exact fit. The second option is microvariability, which is what Seria Gunawan et al. In 2000 saw on a different colliding wind binary system. However, they saw variability on the order of a few millijanskis that seemed to have no consistent pattern. And we are seeing variability on the order of 50 millijanskis that does have a pattern. This microvariability would be caused by clumpiness in the wind and those clumps moving into the colliding wind, the wind collision region. But we are not sure that this can explain what we are seeing. but we cannot exclude it as an option. And the third option is that the model that we are using is simply too simple to describe this system. I have mentioned a few times now that this system is unique and weird. And one of the reasons is that this system consists of two Wolf-Rayet stars, instead of a Wolf-Rayet star and an oak star for which this model was made. Now, this should, in theory, not matter, but it might have some effects that we have not considered yet. But more importantly, it is possible that one of these stars is launching an anisotropic wind. And in that case, this model is not really applicable anymore, as this assumes two spherical winds colliding and not one anisotropic and one spherical wind. We are currently looking into adapting this model to work with this situation, but we do not know if this will work yet. So that brings me to my final one, which is that we are open to suggestions. If anyone has any idea what could be causing this, I would love to hear it because we are running out of ideas. Okay, so that brings me to my summary slide. I would like to say APEP is a very interesting system, which still has many unexplained properties. And we can explain some properties, such as the steep turnover in the spectrum, which can be explained with free absorption. However, free absorption and the model for that evolution over time and the actual time evolution that we observe do not quite match. So it is not quite clear why this should not match and how we could solve this open problem. So there are still many open questions about this, and we are currently writing this up in a paper, which will hopefully be published sometime in the future. So that is the end of my presentation, and I'll be happy to take any questions.
Thank you very much for the great talk. So yes, we already have a question from Simon, I think. Do you want to unmute?
I can just ask my question. Very nice. It's very nice to see a Wolf-Rayet colliding wind binary in action. And your movie is even more spectacular than I had ever anticipated. Only it rotates the other way around as the simulation. That's a little bit of it. You should observe the object from the other side, I think.
I think so, yeah. If you wanted to mesh this one, then yeah, you should be observing.
Yes, this clearly asks for a dynamical model, and what you're doing is mostly statical. So I think that I would be delighted to talk to you about how to do this, and Joe to how to make a dynamical model of such a system.
Okay, great.
Cool. Okay, so we also have a question from Harish. Do you want to? Yeah, go on.
Yeah, have you tried to see what happens to your frequency time variability plot if you try to interpret this as synchrotron self-absorption and the variation as just a variation in the relativistic population?
Yes, so is this what you meant, or?
Yeah.
Okay.
I mean, this is assuming a model for the electrons, a 3D model, and then finding out the free opacity, right? That's what you're doing here. And
yes, this is modeling the free opacity variability, which is, you can see the turnover moving here, but you can also see the intrinsic flux, which is over here moving. That would be because the density of the intrinsic flux depends on the density of the electrons, and that depends on the separation of the star launching the wind and the wind collision region. So that is why this is varying as well. We had to make some assumptions. Yeah. Sorry.
My question is, what if the turnover in the spectrum is because of synchrotron absorption and not free absorption?
Then should probably go back a few slides for that. So far, this is the best fit. Every other model is either too broad up here, or it can't go down quick enough to actually reach this data point and to agree with all of the data that we have. So that is why this is the most likely.
Okay, so you're actually ruling out synchrotron self-absorption.
I cannot rule out that it is happening in combination with free absorption.
Got it, okay.
But if I want to explain it, this is the best explanation that we found so far.
Okay, thanks.
Great, so yeah, Paul, do you want to also ask, you have a question or no? No. You're muted.
I'm really puzzled by that picture of the dust in this system that you showed. Do you have any conceptual model of how this kind of shape could have been arrived at? Is the star wobbling or so?
We do have a model that is described in the Hanadal paper from 2020. And this is I'm not an expert on this, but this is the plot that they show. And the idea is that at some point the dust production has to turn off and then turn back on again to be able to create this specific shape.
Okay.
So I think the idea is that as soon as it moves far away, then the density is too low to be able to, I think this is what they mean by that no dust produced over here. So it turns off, and then as it moves back, it will turn back on again and will start producing dust again.
So basically also the electron temperatures must be quite different throughout the orbit.
Yes.
And that is not in your model of the synchrotron absorption.
Yes, that is so far not included in our model, so we will work on trying to include that as well.
Okay. It's nice work. Very nice puzzle. Good luck.
Thank you.
Great, thank you very much. So thanks to everybody in the first session. So now we have a break, and I would suggest that we all come back at 4 p.m. So we'll start at 4 p.m. sharp with the next speaker. So yeah, enjoy the break.
I did want to mention.
Also feel free to use the Slack channel for questions. Yeah. So
Yes. There was one question in the Slack channel for this last talk. So.
Okay, so I would suggest that so the speakers, if they can go and look at keep the discussion in the Slack channel if possible, because I mean we are out of time for now. Yeah. All right, so I guess we can slowly come. Yeah, we can slowly come back. Yeah, so first I want to just emphasize that please keep the discussion in the Slack channels, and if the speakers can like monitor it so they can answer any questions that they might be there after the meeting. So, okay, so let's start with Alice Booth from Leiden Observatory. So Alice, if you can share your screen. Great. Yeah.
Yeah.
Perfect. Stop. Yeah.
All right, so today I'm going to talk about some recent papers I've been working on with myself and Nienke van der Marel and a few other people at Leiden University. So a major asymmetric ice trap in a planet-forming disk. So why should you care about disk chemistry to begin with? So with ALMA now we're able to look at a lot of nearby protoplanetary disks, and we see a lot of interesting things. I guess the most striking things that we've seen so far is the structures in the millimeter dust continuum. So on the left, this is one of our most observed disks, 163296. And what's nice is here there are multiple rings of dust that might be sculpted by forming planets. And when we look towards directly imaged exoplanets, we can look at these kind of things on similar spatial scales as well. So this is one of the most famous systems, HR8799, and has multiple directly imaged giant planets. So the physical and the chemical conditions in the disks are the initial conditions for planet formation. So this is why we care about disks and why we care about chemistry in particular, because this will set the composition of your forming planets. So the typical disk that we look at with ALMA, this is kind of an array of images of TW Hydra. So typical disk so far. So on the top left, we have the dust continuum, and then we've got some of the more commonly observed molecular lines. So the first thing is that typically the dust disk is very highly structured, and there's no clear one-to-one relationship between the gas and the dust emission. And that's partly resolution limited because these observations on the top left are at a scale of about 5 AU, whereas when we go to gas lines, these are much larger beams. So we're looking at, say, 10 to 50 AU resolution. So the CO should trace the bulk of the gas in the disk where the disk is warm, and then N2H plus is going to trace the colder regions of the disk where CO freezes out. And when we come to some of these more simple radicals, CN, CS, C2H, these are also tracing the disk atmosphere. So what's interesting about these species is that they're actually enhanced to what was initially predicted from disk chemical models. So a lot of evidence is now pointing towards a lot of disks have elevated C to O ratios in their atmospheres. So in these molecular layers, the C over O needs to be between about 1 and 2 to account for the abundances of these species. And this is a lot higher than what we take as the kind of typical solar value of the C to O ratio of gas to be about 0.5. So most disks seem to be depleted in volatile oxygen. And when we go to slightly more complex molecules like formaldehyde and methanol, what we tend to find is that we have low ratios of formaldehyde to methanol. So we like to compare these species together because they can be chemically linked. And we find that the abundance of methyl to formaldehyde is about 1 if it's detected, which is in TW Hydra. And this indicates that most of the formaldehyde is coming from gas phase chemical reactions versus coming from the grains. And then the methanol is cold in this disk. So that means we're seeing methanol coming from the outer disk from non-thermal desorption processes. And these are very inefficient. So most of the methanol actually gets destroyed when it comes off the ice. This is kind of a typical gallery of a disk with ALMA. So the question is, where has all this oxygen gone in the atmosphere? So most some very nice chemical models from Sebastian Kreit came out last year. So this is a slice of a disk, so radius versus height, and these couple chemical and dust evolution. So the color scale is the abundance of CO in the disk. So when you initiate the simulation, you have a CO abundance in the molecular layer of 10 to minus 4. The CO snow line is here at about 40 AU, and this is the snow surface going up into the disk. And over time, you see that the amount of CO in the gas phase decreases. So we're depleting the CO and thus the oxygen in the disk. And this means that the bulk of the gas has got a CO ratio greater than 1, and most of this volatile oxygen is locked up in species like CO, CO2, methanol, in ices, in what we call dust traps. So over time, the dust in the disk will drift inwards and trap in these types of rings and asymmetries that we've seen with ALMA already. So I'm going to talk about the IRS-48 disk today that we've had some nice ALMA observations of recently. This is a big star, so it's warmer than, say, the disk around TW Hydra. Two solar masses relatively nearby. And these are images of the CO and the continuum, I think, taken with ALMA band 9. So we have gas throughout the entire azimuth of the disk, as you can see here on the left. And then on the right, we have the millimeter dust. And these grains are mostly constrained to one side of the disk. So this is one of the most extreme asymmetries that has been seen in a disk so far. And then there's also a cavity in the dust out to about 60 AU and the gas to about 30 AU. So this is quite a nice disk to observe, because instead of having a lot of intricate substructures, we just have one clear substructure where we have dust here and we know that we don't have large dust on the other side of the disk. So it can make disentangling what we see in the gas as a terms of gas phase chemistry or gas grain chemistry a bit easier to distinguish. So we got some observations that cover multiple lines. So this is the first set of molecules are sulfur-bearing molecules. So this is SO2, an SO2 isotopolog, and SO. So these are the first detections of SO2 and in a protoplanetary disk. So it tends to be in disks that, again, sulfur-bearing species tend to not be observed very often. We mostly see CS, but not the oxygen-bearing ones. And you can see that it's quite striking that the molecular lines are also asymmetric, just like the dust. So they're sharing a similar spatial distribution, and there's quite a lot of sulfur if we're detecting one of the isotopologs quite clearly as well. So the detections of these molecules, and we don't have any CS detected, and we cover it in some data, indicates that we have a low CO ratio, so less than 1. And there's actually a lot of sulfur. We can account for basically almost the entire volatile budget of sulfur that you'd expect to see in a disk. So the solar abundance is about 5 times 10 to minus 5, and 10% of this should be in volatiles, and we can pretty much account for the bulk of it, which is a very nice result in itself, but the asymmetries is particularly interesting. So what we also do is we also cover lines of methanol and formaldehyde in the data set, and quite amazingly, they've detected 6 different lines of methanol and formaldehyde in a disk, which I think is quite striking to see all of these molecular lines together. And they're all asymmetric as well, like the SO2. And we're able to cover a range of upper energy levels as well to learn a bit more about the excitation conditions in the gas. So if you have a look at the azimuthal profiles of these sources, so you take basically an intensity cut all the way around the disk at a particular radius, you can compare how the different lines are structured. So we find that the methanol and the dust here in the gray and orange are pretty much co-spatial, and then the formaldehyde and the SO2 have a slightly larger azimuthal extent. And this could be just due to optical depth effects or viewing angles, or we might have different emitting regions of the molecules, but it's not something we can disentangle right now with the data that we have. And we're also able to do a lot of excitation analysis on the lines as well. So basically with formaldehyde and methanol, we can do rotation diagrams and find that the lines are quite warm and between 100 and about 200 Kelvin. And the ratio between these is 6, so it's quite high, methanol to formaldehyde ratio of 6. And that indicates that we're seeing methanol or formaldehyde related to an ice origin rather than gas phase chemistry. So to kind of tie things up, we have the chemical origin. All these comes in a warm disk as well. I should mention that this disk is quite warm, so the only way we can have these complex molecules is if we inherit them from an earlier time, because we can't form methanol on the disk because there's no CO frozen out because it's too warm. For more details on that, I would reference my paper that came out a couple of weeks ago in Nature Astronomy. And then we actually detect more comets on the disk as well. So we have a detection of dimethyl ether as well, which is really exciting. And we have a master's student in Leiden working on this. And we have a preliminary kind of value of about 10% for dimethyl ether to methanol. So the origin of the emission in this disk, the best way to explain the asymmetry is if the ice reservoir is constrained to the large grains, so we just see on one side of the disk. And then because we have a cavity and the irradiation from the central star is hitting the edge of this cavity, we can have high enough temperatures to sublimate the ices. But we can also, because this is the vortex, we can have a lot of turbulent mixing, bringing ices up from the midplane up to higher levels in the atmosphere where it's warmer, and that all results in the sublimation of these species that were previously locked up in the grains. So what does this mean for forming planets in the disk? So take this cartoon of the disk, we're going to inherit ices from an initial dark cloud stage. So we start with ice in our disk already, and when it's forming, gas in the outer disk probably has a high C/O ratio, whereas gas going through the cavity probably has a low C/O ratio. And then because we have complex molecules, it means we also have the potential for prebiotic chemistry in the disk. So this is kind of the picture of what we think we're seeing in this warm disk, and probably holds for other warm disks. And I think I'll just leave my conclusions up because I think it's at about time.
You have like 15 more seconds if you want to.
All right. So we show quite a clear link between the gas and the dust drop structure in this disk, and both of these simple and complex molecules can originate from the ices. So we're not seeing chemistry that's driven primarily by gas phase reactions. Instead, we're looking at sublimation of ices. And we can account for most of the sulfur we'd expect to see in the disk. And the fact that we have complex molecules in a warm disk kind of favors that we're inheriting molecules from an earlier, colder stage of evolution. And we show that potentially the gas going through the cavities of these warm disks actually has a low C/O ratio that could be closer to solar. And that's very different to what's observed in the molecular layer of disks further out, say, and in the other sources. So yeah, thanks for listening and letting me talk to you today.
Great, thank you very much. This was a very nice talk. So are there any questions? Yeah, feel free to put them in the chat or the Slack, or just raise your hand. So once people are thinking about it, I was wondering about, has anybody actually detected the planets that you say they might be there? Or are they, do you know that they are there, or like have they been detected by
this is more of just like an illustrative thing. To form the asymmetry that is in the Iris-48 disk, I think it can be explained by a few mechanisms, but one is that you have a planet or a companion on the, I guess, in the cavity. So that can indirectly explain what's happening in the disk. But yeah, no, this is just illustrative, really.
No, that makes sense. I was just wondering in case, yeah, that's really cool. Any questions? I was also another question I can ask. So you said that it is probably those complex molecules are inherited instead of the reset. So I don't know. Did you look at modeling this? Or
yeah, so we ran the models for the other paper, but for this, basically the dust temperature in the disk is above 30 Kelvin, so we can't form methanol in the grains in the disk.
Okay. No, that's actually really cool. Yeah. Thank you very much. So we also have a question from Floris, right? Do you want to unmute? Yeah.
Yes, can you hear me despite the loud rain on my roof?
Yes, it's great. Yeah.
Great. So super stuff, Alice. Congratulations. I was interested in how you were, if you had any plans to model this further. You mentioned something like optical depth effects and excitation you went by and so on. I'd be curious what your plans are in that direction.
Yeah, I don't think we quite have the tools yet to do the kind of 3D modeling that you'd want to do for a source like this and with the imagery, but we do have we have 2D models of you could look at slices of the disk, but modeling something in full 3D. I guess the radio transfer tools exist, but maybe I think it could be possible to do, but I'm not sure.
Well, the 2D would be a good start, I suppose.
2D is a good start.
Yeah. Good. Looking forward to the results.
Thanks.
Great. So, Martijn, are there any questions in Slack?
No questions on this talk.
Yeah, I can't also see anybody raising their hand or anything in the chat. So I guess we can move on to the next person because we are almost done with the time too. So thank you very much again, Alice. And let's move to Batsal Panwar from UVA, talking about characterizing exoplanet atmospheres. So please take it away. Yeah, you can start whenever you're ready.
Hi, I'm Vatsal. I'm a fourth-year PhD student working at University of Amsterdam. And I would like to thank the organizers for giving the opportunity to talk about some of the work that I've been doing to characterize exoplanet atmospheres using ground-based observations. So earlier today, as Nuria introduced, one of the ways to study exoplanet atmospheres from ground-based observations is to use really high-resolution spectroscopic observations and measure the changes in the depths of lines that you get out of these observations as the planet transits the star. Well, another common way to also study exoplanet atmospheres is using low-resolution spectroscopy. So what you see here is sort of a toy model for a planetary transmission spectra, which is essentially the measurement of the transit depth of a planet as it transits its star. And you can see that in a spectra like this, you can observe signatures due to elements like potassium, sodium, or molecular signatures of water even in the planet's atmosphere. And you can do this from ground, essentially in two windows, which are transparent in the Earth's atmosphere, in the optical and near infrared. And what I have been doing is using two instruments. One is GMOS at Gemini observatories, which probes these observations in optical, and in near infrared using MOSFET, which is another similar sort of instrument, but optimized for the near infrared wavelengths. So let me really explain to you in brief how traditionally these observations work. So what you essentially have is a multi-object spectrograph. And what you do is you observe a target star, essentially the star which has a planet, and a comparison star or reference star with similar brightness or spectral type in the field of view of your instrument. And what you get is a spectra that looks something like this. What essentially you're doing is you're trying to measure the spectra of the star in time for both the target and the comparison star in a way that you cover nearly the same wavelength ranges for both of these stars. So essentially what you can do is you can measure these transit signals by correcting for the effect of the Earth's atmosphere or systematics due to the instrument for respective wavelengths. And this actually works quite reasonably well. In fact, in some cases, when you have a really optimum comparison star, you can get precisions from these instruments which are quite comparable to what you would get from HST, which is quite exciting because you have a very complete coverage of the transit, and you can even have a really high precision on the timing of these measurements. However, these observations have some very intrinsic severe shortcomings, which I would like to point out by just revisiting some of the very basics of these observations. So what you see here on the right is the kind of light curves we have to deal with. This is a target light curve, which essentially you can, just by eye, you can see the signature of transit. And this is the comparison star that was observed for this kind of observation. And you can see that there is an effect on a very long-term scale, which is because of the air mass. And there's also more high-frequency variation. So the one such variation you can see is sort of an odd-even effect in these light curves, which is due to the instrument itself. So one problem that you can immediately sort of think when you say, okay, you're going to use the comparison star as sort of a reference or as a normalizing factor to remove these systematics from the target star. Well, the comparison star could be variable. And just this operation of normalizing by the comparison star and doing a sort of differential photometry could actually end up adding systematics in the target star. And moreover, since through the strategy you need a sort of a suitable comparison star in the field of view of instrument, this technique automatically kind of limits these observations to targets which do have such comparison stars. So for example, really bright targets with no similar spectral type or brightness comparison star in the field of view of the instrument are kind of precluded by these by this strategy. So what we really need a new way to deal with these systematics and to be able to do these observations without having the comparison star. Well, one way to just bypass this sort of need to normalize is to just use this comparison star as an input to one of your systematic model. So what I'm doing is using a Gaussian process model, which I won't go much into detail, but what it essentially does is uses the information present in the comparison star as a sort of prior to model the systematics in the target star. And this is the kind of model you get. So you can really clearly fit the systematics and the planetary signal quite well. Well, going one step further, you can see that you already have the systematics information in the target light curve itself. So you don't essentially need the comparison star. So if you were to remove the transit signal from this light curve, what you essentially end up getting is a sort of a vector that contains this information, which you can use as a prior to your model. So again, using a Gaussian process model in my case, and you can use this to fit the spectroscopically binned light curves. And that can actually help you get the transmission spectrum without using the comparative star at all. And this is actually quite provocative, but if you see that by using this method, so here is an example of one such observation that I've been working with, and you can use this method to fit for sort of both low and high frequency variations. So here what you're seeing is spectroscopically binned transit light curves going from blue to red. And you can fit for both these systematics in both time and wavelength dimension. And once I remove this, you can see that you can clearly recover the transit signal quite well, which shows that this method of not using a comparison star at all works actually quite well. And if I just compare the kind of residuals I get for these models from the method that I have been using is just fitting for the target light curve and the traditional way, which uses a comparison star light curve, I actually get an improvement on scatter by almost 60%. And it is quite expected because you are not adding up the systematics or adding up the noise from the comparison star in the target star in this new method. And just like sort of validating these this method on synthetic light curves. So here what you see are different posteriors I get for synthetic light curves when I use both the method that I've been developing and the traditional way of using the comparison star. You see that in the red posteriors, you recover the original transit parameters, which are marked by the green line in much better accuracy and precision as compared to the old.
3 minutes.
Yeah. So here's an example of my application to one such observation that I've been working with is for a warm Neptune HAT-P26, and it's quite bright in the near infrared. So here's an expected model for a cloud-free atmosphere. And what you essentially get from HST light curves is a muted spectrum, a muted feature of water in the atmosphere, and in the optical sort of indication of clouds in the atmosphere. But when I actually use the GMOS observations for this planet, we actually confirm the presence of a cloud deck in the atmosphere of this planet. Going forward, it's also necessary for measuring accurate transit depths for planets around really active stars, because here, as an example, you can see WASP-19. It's an ultra-hot Jupiter orbiting a star which varies at the timescales of almost 10 days and about 2 to 3%. And this can actually really change the planetary spectra. So here's an example of what happens to the transmission spectra of the planet when you have spots at different contrasts and different activity levels, and it can affect the transmission spectra up to almost about 0.1% in this case. So I'm just going to show you some of the measurements I've been doing. So my method actually really yields absolute transit depth measurements. So if I compare multiple epochs, so this is one epoch for this planet, and this is another epoch, and this is third epoch. So you can clearly see that this effect of the planet, the stellar photosphere changing over time is reflected quite well in the final transmission spectra of this planet. And just going further, doing a first order analysis, I can see that the slope of the transmission spectra also changes with the level of the transmission spectra, which also agrees quite well with what we see in the test light curves for this planet. So with this, I'll leave you with the conclusions. So I've developed a new method that does not rely on comparison star at all. And this kind of gives you a transmission spectra which is absolute and more accurate and precise. And it also opens up the possibility of studying really bright targets from ground-based observations. And we can also observe effects of stellar variability over multiple epochs. Yeah, I'll take any questions. Thank you.
Thank you very much for the very nice talk. And okay, so we have plenty of time for questions. Are there any questions? So please feel free to write in the chat, Slack channel, or raise your hand. Okay, so once people are thinking, I'll ask a question. So I was wondering, so have you actually done I don't know, applied this method to other systems or not? Yeah, I was just wondering. Like,
yes, yeah. So what I'm actually working with is a survey of like almost a dozen planets that we have observed using GMOS and Mospire, and I have been working on some of the other targets as well. So in one of the targets that I've been working with, we actually recover the signals that we have kind of previously have indications for. Yeah. So I have actually applied this to other cases as well.
Very cool. Cool. So we also, so Harish, do you want to, yeah, go on.
Yeah. My question is about, so when you do the Gaussian process analysis, you, of course, in this case, you know where the transit is. And so I'm curious what happens if you don't know where the transit is. Like,
yes, yeah.
I guess you'll have to tweak things a little bit.
Yeah. So it really, because so the effectiveness of this Gaussian process model really depends on the timescales of your noises. So if you have a transit which is say a bit shallower, for example, and your noise also varies with the same scale, you will need to at least inform it where the transit is occurring.
Sure. Yeah. So I was trying to get at, like, what are the covariance functions you're using for this? I guess it depends on that, right? What?
Yes. Yeah. So I use this sort of an exponential covariance function in this case, where it kind of tells you that, okay, if the points are really further apart, they're not as well correlated. Yeah.
And you use some knowledge of what's the time scale of the systematic errors.
Yeah, I fit for that, but you can actually have some priors on that as well if you have information about that a priori. Yeah, but for example, for the transit model itself, you kind of need to be sure that at least your mid-transit time is not off the charts, because you could end up fitting the whole transit and the systematic. Yeah.
Thanks.
Cool. So we also have a question from Oliver. Do you mind unmuting it?
Yeah. Hi, Vatul. Thanks for the nice talk. As you know, I don't know much about exoplanets, but I was wondering, you had this slide which you showed the posterior distribution functions, which you cut out, and then this green line.
Yes.
And then for some of them, the green, the PDF that you get out doesn't really match the green line at all. Is this something which is to be expected?
Yeah, so this is just a comparison of fitting a simple transit light curve by the old and new method. And yeah, you kind of, because in the blue case is what you're doing is you're adding up noise in your original data set because you're trying to remove something else. And that kind of also gets reflected in the final sort of white noise parameter that you get for these fits. Yeah.
Mm-hmm. All right, thanks.
Cool. Okay, so Martin, are there any questions in the Slack channel?
Nope.
No. All right. So I can't also see anything here. And yeah, so I would recommend everybody to write your questions in the Slack later if you have more. And now we can move on to the next person. So yeah, so the next person is Harish Vedanta from Astra. So do you want? Okay, perfect. Yes, great. Yeah, you can start anytime.
Okay, so I guess everyone can see my screen.
Yes, it's perfect.
All right, thanks, Pune. Okay, I'm Harish, and I'm going to basically tell you about using radio astronomy to say some interesting things about exoplanets and brown dwarfs. Of course, this work which I'm going to be presenting did involve people other than me who have listed here. Okay, so I thought I'll take you on a thought experiment because most exoplanet work is done with optical or near infrared, and so assume that you are an hypothetical alien on some other planet and you are actually looking at the solar system, right? And so you're just taking spectra as astronomers do, and as is typical on the Earth, you start off in the optical because the star is brighter, and so this is something you would see. So I have flux density in the y-axis, wavelength in microns on the x-axis. This is what you would see, and this is basically the sun's spectrum. Just notice that I have units of Jansky on the y-axis and microns on the x-axis. So maybe I'm not going to make either the optical or the radio astronomers happy with these units. But there you have it. Anyhow, so you would be excused to think that, well, if I go to longer wavelengths, I'm going to see something like that because your civilization has figured out the Rayleigh-Jeans law. But of course, if you go ahead and measure it, then you see something like that, right? And so you scratch your head and you're like, well, what's happening at these long wavelengths? You put a few good theorists to work, and then they come out with the answer. They say, well, is basically the high energy kind of almost relativistic population in the corona of the sun. And that will also be reflected in the X-rays, which I haven't shown here, right? And well, that kind of agrees, and you have intuition for that. But this huge bump you see here, well, that's another ball game, right? So you figure out that this comes from the sun. Well, it turns out that this bump is rather strange. It is highly circularly polarized. And you figure out that it's actually cyclotron emission. So this is the emission of charges spiraling in magnetic fields, and it doesn't even come from the sun. It's way brighter than what the sun is at these frequencies. It actually comes from Jupiter. And if you monitor that over a period of time, you find periodicities, and you work out a bunch of different things. Because cyclotron emission tells you what the magnetic field is at the point of emission, you actually find out that this planet in this solar system has a magnetic field. You measure its magnetic field strength. The emission is also beamed, so you get a lighthouse effect. So you measure the rotation rate of the planet. And also you find out that a component of the emission is induced by not just the rotation of the planet, but by the presence of a moon around the planet. So in this case, it would be Io and Ganymede if you have the sensitivity. So you figure out that the planet actually has moons. And as I'll say a little bit later, you also figure out the acceleration mechanism, which is creating this radio emission. So you work out a whole lot about a planet in this system by just looking at low frequency radio data at these very long wavelengths. A lot of things probably you couldn't work out by looking at the optical band. Well, of course, once in a while the sun goes crazy and you get a huge burst and everything breaks loose. I won't go into this, but it's something we're working on also. You can actually figure out a whole lot about about what's happening to the planet by looking when the sun goes crazy. You actually figure out the presence of coronal mass ejections, relativistic beams, what we call energetic particle events. They're energetics and they're read by radio observation. So that's kind of in a nutshell of what we're trying to do with this radio data. Now I'm going to make the case that with LOFAR, and I hope LOFAR doesn't need an introduction here, we are at the right frequencies, which is the low frequencies, the long wavelengths, and we have enough sensitivity to kind of open up this frontier. So it's not merely a thought experiment, which we just did. We could actually point our radio telescopes to other systems and then do the same things, which I just spoke about doing. So with LOFAR, I would say that this box here on the mass ladder, so going from really cold brown dwarfs to kind of Jupiter mass planets is now within reach. And I'm going to demonstrate that that is the case. Okay, so what's so unique about LOFAR and going to low frequencies? What I've done here is I've plotted the cyclotron cutoff frequency of planet-like objects on the y-axis. So what is this? Well, this is the frequency below which you need to be observing to detect this planet, right? And if you measure the cutoff frequency, you measure the magnetic field of the planet. On the x-axis is age, and these are basically dynamo models that are predicting the magnetic field strength of planets. So these are theoretical models. Most of the previous radio observations or detections of these brown dwarfs came from very high frequencies. So they were really measuring this 100 Jupiter mass objects. They are really the lowest mass stars and some warmer brown dwarfs. The LOFAR range is pretty interesting in that it completely opens up the whole low planetary mass brown dwarfs and exoplanet regime, right? So this is the kind of objects you're going to find in the sky if you went with LOFAR. So how do we do that? Well, it turns out that when you're looking for really cold objects, maybe you haven't found them in the infrared yet, because the infrared emission is thermal, and that you all know that goes as effective temperature to the power 4. So you get to a very low mass object, maybe you haven't found it in the infrared. So what we're doing is directly discovering them in the radio itself. So we're looking for that cyclotron emission directly and kind of departing from the conventional wisdom, which was that, WISE satellite or what have you finds a cold brown dwarf and you point your radio telescope in that direction. So what we're doing, I'm trying to demonstrate what we're doing here with the first discovery we made. So here is a radio image made with the LOT survey data. Tim Shimbel spoke about this really nice survey of the sky, which is going around 44 megahertz. So what you see here is Stokes size, so total intensity, and most sources you see are extragalactic. They're relativistic jets, except for the one circled there. Of course, that doesn't stand out in this image, but if I now look at the same field in circularly polarized light, which is what you get from cyclotron emission, all the extragalactic sources are gone, and I'm left with this one point there. And so that immediately tells you that you're seeing cyclotron emission because it's highly circularly polarized. Now you go in the optical, so this is pan stars of the same field, R band, and there's nothing there, and that's good news because it tells you you're not looking at a star in this case. Okay, so it's highly likely you're looking at a very cold brown dwarf if it's not in pan stars and it's circularly polarized. Yeah, so I won't belabor the point. We got infrared data, we detected it, we found its proper motion, all of that, and finally got some spectroscopy on the object, and it turns out that the object is indeed a very cold brown dwarf. It's T6.5. The unusual thing about this, and this is the fun thing when you directly find things with the radio, is that its distance is 65 parsecs. So that's very far away compared to what we would have expected to find as our first object, right? We would have expected something nearby and bright. And maybe this number, which is the radio luminosity, doesn't mean much to you, but for many people here, but it's about 2 orders of magnitude brighter than what you would have expected based on previous observations of sort of similar objects, of which we only have a few. So it tells you that when you go looking in the radio, you actually find these really bright objects, and there's something strange going on in them in terms of their acceleration mechanism that is making them bright, and that's pretty interesting. So we found a second one. So that's good news. As you look at more data, you find more of these objects. Of course, in this case, this one was already found by the WISE satellite. So this was a known object. And in this case, instead of the full exposure image, I'm showing you the radio flux density versus the time. And it's about 8 hours. And the box and the curve and the points are at 2 different binning, basically. And so you see that this object sends out 2 different pulses. And this is interesting because of the lighthouse effect, which I mentioned. So once you get these pulses, you can work out the rotation rate of the object. And you can do a lot more, as I'm going to show in a bit. Okay, so where is all of this going? So now that we have figured out a way to discover these objects directly in the radio, what can we do? Like, how can we make that thought experiment really come true? Well, we do that basically by following up these objects at slightly higher frequencies. So here is a spectrum of Jupiter's emission. So y-axis is flux density in Janssy, x-axis is frequency now, not wavelengths. And what you see that you kind of see a broad spectrum, and then it abruptly cuts off at around 40 megahertz. That's what you measure for Jupiter. And the reason for that is the lower frequency emission is coming from further out in the magnetosphere where the magnetic field strength is lower. And as you get closer and closer to the surface, you get higher and higher cyclotron frequencies, but nowhere can it be higher than the value at the surface itself, right? And so it just cuts off. And the moment you know where it cuts off, you measure the magnetic field, you know roughly the radius of the object, all of these brown dwarfs and Jupiter supported by degeneracy pressure. So you know their radius. And perhaps you can measure their mass, you can measure their temperature with infrared observation. So you have all the pieces together, you have a measurement of magnetic field with radio, and you can start asking the question, what determines a planet's magnetic field? Like, is that its rotation rate? Is it its heat flux? You can start testing these models. So that's where all of this is going in the future. The second point, which I want to mention before ending, is where we can actually also figure out the dominant acceleration mechanism. So what I'm showing here is a toy model for 2 different ways to accelerate electrons. And you see that in Jupiter. And one way on the top, which is shown on the top, is Jupiter basically going solo, right? And so what Jupiter is doing is it's a big giant magnet and it's rotating. So it's basically like a bicycle dynamo. It's generating a big current. It's a rotating magnet. And in this case, the coil in the dynamo is basically the plasma in the magnetosphere of Jupiter. So it sets up this huge current system. And then that is what creates the radio emission. And because of that lighthouse effect, you get these pulses every rotation period. In the second case, this is how you figure out in the thought experiment that actually there's a planet, there's a moon around Jupiter. That coil is basically a conductive body, which is Io. right? So in this case, Io is inducing, is doing the Faraday induction in this dynamo model, and then that is creating the radio emission. And in that case, you don't get perfect periodicity, you get a beat between the rotation period of Jupiter and the orbital period of Io. And that's what you see here. There is some periodicity, but you see it at the beat period. And so you keep monitoring these objects. Maybe we're going to find, exomoons, or I don't know how to name them, what planets around brown dwarfs, I guess. We'll be able to detect those by, timing those pulses over a long period of time. So that's where all of this is going. So yeah, so I'm going to end with a nice artist impression we made for the first discovery and take questions.
Thank you very much for the very nice talk. It was really interesting. So are there any questions? Yeah, feel free to just raise your hand or put it in the chat or Slack. And so, yeah, okay, so we have a question. So Jean-Michel, do you want to ask?
Thank you. Yeah, great talk, Harish. So I wanted to know, you mentioned those two objects for which you have detections, and did you measure the rotation rate for the subject? And when you compare the rotation rate, if you measured it to what we know about those brown dwarfs, how does it compare? Do you see any? Do you see them as outlier or in the bulk part of slow rotator or fast rotators?
Yeah, so for the first object, we haven't found pulses yet, and it could be because it has a very specific geometry where that lighthouse beam is always visible to you. And for the second object, we do have pulses, and so we need to observe it for a few more periods to be sure what the period is. It's hard to get a good rate with just two pulses, but even if you take that at face value, it's about 3 hours separated, and that's not atypical of what you would expect from this brown. I mean, a 3-hour rotation period is quite normal for a brown dwarf. I mean, Jupiter is 9 hours, so it's roughly in the same ballpark, I would say.
And if I can follow on that, okay. So in the solo version that you presented, you had 2 pulses each time. Why is it that you have 2 consecutive pulses and then the period?
So are you talking about the top?
Yeah, sorry, the induced, right? Yeah.
The induced. Okay, so what's happening in the induced is pretty interesting, because you have currents flowing only at a particular azimuth. That is the azimuth of Io in this case, right? It's not there everywhere in the magnetosphere. It's there only in a specific position. That combined with beaming means that you only see the emission come towards you when Io is at a particular longitude. So you're really taking the top case here and gating, and the gate opens when Io is at the right longitude. So that's why how you get the double modulation. It's the rotation rate of Jupiter modulated by the orbital period of Io.
But you see 2 spikes.
Oh yeah. That's because Jupiter is rotated twice. I mean, in this case, I just put in some random values for the orbital period. Right, this is not exactly.
Okay.
Yeah, I've just put in a random. I put in the rotation rate of 3 hours and an orbital period of 2 days, or something like that. Right?
All right.
And so in that case, in that window of opportunity, you get 2 rotations of the brown dwarf. Yeah.
Thank you.
Cool. So also we have a question from Flores. Do you want to unmute and ask your question?
Great stuff, Harish. Congratulations. I was curious, so you can measure the strength of the magnetic field from this cutoff frequency. I was curious if you can also say something about its direction. As you may know, in Jupiter's case, it is actually a bit misaligned with the rotation direction by 10 degrees or so. I was curious if this would be possible to see also in other systems.
Yeah, we can. Actually, you can work that out from Jupiter too, just from the radio data. It's a little more complicated in that you also need to figure out the refraction of the radio waves in the source itself to be able to confidently say that there is magnetic, or this is the magnetic obliquity. So you basically have to model the emission geometry and the propagation geometry, and you could do it. So in principle, yes, you could do those things. The expectation is that almost all objects will have some obliquity, because I think our current understanding of dynamo theory is that it's hard to produce a dynamo with no obliquity at all.
Yes, so I think so. Do you need then a multi-frequency observations of this for this, or what what other information do you need?
Yeah, I think you need multi-frequency. Yeah, and we're going to do that anyways, because whenever we see, we are going to go to these the surface magnetic field, right? So we're planning to have the data anyways, and we're already taking pilot observations with GMRT, going all the way up to 600 megahertz.
Great, thanks.
Cool, thank you very much. So we don't have that much time. Martin, I don't know if the question is quick. I could take one more question. So Martin, do you want to actually ask your question? And
yeah. So I was curious. Like all these rotating planets remind me a lot of pulsars. So I was wondering, how can you differentiate between a very slowly rotating pulsar and a planet or a brown dwarf?
That's very interesting. So it's something we worry about as well, because when you don't see something in the optical, you worry about if this is a pulsar or a brown dwarf or planet. Well, the infrared detection statistically tells you it's a brown dwarf. It's very rare to find a pulsar which is circularly polarized and which has a brown dwarf right there in orbit around it. And the brown dwarf just looks normal in that it's not heated because of the pulsar wind, right? And so in this case, it's almost obvious that the emission is coming from brown dwarf. There's no pulsar. The other thing is we've actually made we have taken an inventory of circular polarization from pulsars, known pulsars, and they all tend to be less than about 30%. So it's kind of hard to get broadband circular polarization close to 100% as we see from these planets and brown dwarfs. So based on those two, you can almost conclusively rule out that there's no pulsar in this system.
Interesting, thank you.
Great, thank you very much. And it was very nice to have the discussion. Now I think we should move on to the next person. So the next person is Joseph Baja from Leiden. Do you want to share your screen?
Hello, thanks. Okay, I will share my screen. And here is my...
Great, so you can...
Can you see my slides?
Yes, but it's not full screen.
Yeah, nice. It should be.
Oh, yes, it's perfect now. Yeah, you can start whenever you're ready.
Thanks for having me. So I'm Josef Varga from Leiden Observatory, and I'm working with VLTI Matisse data. So Matisse is an infrared interferometer, which has spatial resolution of around 0.3 to 1 AU. So we can look at the innermost parts of young stellar object disks. So in my talk, I would like to present some new results on the silicate content inside the disk, inside the very interesting object. So let me start. So yeah, I'm working with, so the context is planet formation. So terrestrial planets form from tiny dust grains. And the question is how? Yeah, and yeah, there are a lot of steps involving how this great transformation occurs, because there is a very high very big change of spatial scales, going from micron-sized grains to the several thousands of kilometer size of an Earth-type planet. And I'm working with this part where we see these tiny dust grains, silicates, also carbonaceous grains. So what happens to the dust in planet-forming disks? We know that the initial grains can transform, so they can grow, they can stick together, and also they can transform to crystals, because the dust which is found in the interstellar matter is mostly amorphous. And that we can look we can observe this if we observe the mid-infrared spectrum of these disks. And if we have an instrument like MATIS or the predecessor MIDI, we can have spatially resolved spectra. So we can have a spectrum which comes from the inner part of the disk inside a few AU, and having another spectrum which comes from the outer part of the disk. Or we have the full disk spectrum, and if we subtract the inner disk spectrum, then we get the outer disk spectrum. And it was nice discovery that in some disks it was observed that the inner disk predominantly or not predominantly, but has a higher crystalline fraction and higher fraction of large grains than the outer disk. So that's that meets our expectations. And now this was the past with an instrument which could combine only two baselines at two telescopes at once. But now we have MATIS, which delivers six of these inner disk spectrum at the same time at one observation, each with different spatial resolution. So we can do a lot more than this, and we can measure much better the spatial distribution of these ice grains. So these are the mass absorption coefficients of the grains we consider. This is the standard mix of silicates that is usually used in these studies. So one should pick these spectral templates and combine these to get a fit to the whole disk spectrum. So we have these. By the way, these materials are found on Earth. So these silicate minerals are also very abundant, and that's by the way, that's maybe highlights the importance of observing interstellar silicates. That the crust of Earth is made of so much of the crust of Earth, 90% or so, is made of these silicate minerals. Oh, okay. So we have the olivine and pyroxene. These are these amorphous grains. We have the forsterite and enstatite, which are crystalline, and also silica. And for comparison, I put the pH polycyclic aromatic hydrocarbons here. But yeah. So they also have this thing, but those are not silicates. And you can spot that there are two kind of lines. So the solid lines are for small grains, and the dotted lines are for big grains. So grain growth has a big influence on the spectral slope, spectral shape. So with these templates, we can characterize the composition and also the mineral composition and also the grain size composition of the dust. Okay, so I would like to introduce this case of HD 144432. This is a Herbig A-type star. It's a kind of normal disk with normal Young-Stellar object disk. This was nicely fitted with using the Spitzer data, and also I put here this MIDI data where it shows that the different inner disk spectra shows different shapes, so different composition. So let's see. Now this is the MATIS data. So as a quick recap, so these are interferometric spectra. We call it correlated spectra. So these come different regions from the disk, If we move towards the bottom, we get less flux, and we observe the more and more inner parts. And what is happening, that the shape changes. So this part diminishes, while this part is not diminishes as quickly as this part at the short, at this peak. And like in this red spectrum, the 11 micron peak is higher than the 9 micron peak. So the aim of this study is to have a consistent modeling of the disk geometry and the silicate emission at the same time, and the characterize of distribution of silicates, and to measure where are the crystals located and where are the amorphous grains. So we took a simple disk model, the Chiang-Goldreich model, and we modified it to include the silicate opacities there, and to account for the interferometric spectra. So this model contains a midplane and the surface emission, and we have power law temperature profiles. And also we put the mineralogy, and the radial mineralogy gradient is a step function. So there is a Q jump radius, and inside there is the inner disk mineralogy, outside the outer disk mineralogy. So let's see the result. So this is the result. So the dashed lines are the model, and the solid lines are the data. This black line is the single disk spectrum, as Spitzer would see it, but actually it also comes from Matisse. And you can see that the fit is quite good, and this is the corresponding disk structure. So this model, yeah, it's a tweaked model. It includes a gap. You'll find that without a gap, it is very hard to produce these shapes. So yeah, it seems that there is a disk gap, and the Q jump, so the mineralogy jump occurs at around 1.7 AU. So that's where are the crystals located? Inside here, inside 1.7 AU. And the other thing, what is the composition? So in the inner disk, we have mainly small pyroxene plus small crystals, and the outer disk has mainly small olivine and pyroxene, and a little amount of crystals. But here comes the complication. If we want to fit the SED, so this is just a plot. It is not a fit, but the plot of this model, which I just showed, to the SED, and yellow is the model curve, and it doesn't fit, especially in the near infrared part. So yeah, we have still some problems here, and so in order to reach a better, if we try to fit only the SED, then the silicate feature is not well represented. So the silicate shapes and the spatial structure is not fitted well. So there is a question how to fit both the SED and the silicate data with the interferometric data, the Matisse data at the same time. And there are other issues or other interesting things we faced, that we have 3 measurements with Matisse now, and there is a time variability of the shape of the spectrum, and also the Matisse data indicate asymmetries. So still, yeah, there is still a lot of work needs to be done, and I will conclude now. So the inner disk mineralogy can be very specific, and a new Matisse N-band observation can put strong constraints on both the geometry and on the dust distribution, but the modeling is challenging. And the case of this young star AG144432 highlighted that the situation is more complex than we thought, because we have asymmetries and time variability. Okay, thanks. Thank you for your attention.
Thank you very much for the nice talk. So yeah, we have some time for questions. Yeah, are there any questions? So please, yeah, put them in the chat or just raise your hand. And so before people asking their questions, I was wondering, so do you know what, or like, have you done any modeling on what is the origin of these asymmetries that you mentioned for the HD 14? Yeah.
Yeah, okay, I don't have the, yeah. So when I modeled, the asymmetry is included as an azimuthal modulation. So in azimuthal direction, one part of the disk is brighter and the other part of the disk is darker. And that easily represents the data, but the nature is uncertain. So it can be. There was another study of AG163-296, and in that case we assume that it can be a vortex which orbits the star.
Cool. So and the vortex, I don't know. So I was just wondering, what would be the reason that the vortex? So is it a planet, you think, or I don't know? I'm just thinking. Or
yeah,
or
planets can induce vortices. Also, planets can induce these crescent shapes of asymmetries at Lagrange points.
Cool.
And in that case of AG163-296, we in the modeling, numerical modeling, the density gradient at the inner edge of the dust disk induced the vortex.
All right, that's cool.
So these density gradients can induce asymmetric shapes.
Oh, great. Yeah, thank you very much. All right, so I don't see any questions here. Martin, do you see any questions in Slack?
No, nothing on the Slack.
Okay, cool. So in that case, I think we are almost there with the time, and we can just move to the next person. So the final talk today is by Dirk van Dam from Leiden Observatory. So please share your screen. Is Dirk here?
Yeah, I'm here.
All right,
Can you
perfect.
see my screen now?
Yes, it's great. Yeah, so
all right.
Thank you.
All right. Hello, everyone. My name is Dirk van Dam, and I'm working on a project together with Matt Kenworthy that's called Beyond Circular Eclipsers. This is a light curve modeler. So I'm going to give a little bit of an introduction about the subject and talk about circular eclipsers, non-circular eclipsers, then how the software package works, and give some concluding remarks. To start off with, let me minimize this so that I can see this properly. So the discovery of exoplanets, as we all know, has been rising significantly over time. There are many detection methods to do this, of which I've listed a couple here, but I'm going to be focusing on the transit method because that's where we find our light curves. So for the transit method, we use lots of survey telescopes. So a few examples are listed here. But the problem that we find is that we have enormous amounts of data because these telescopes are taking multiple images every night, and we have multiple telescopes that we can query. And there's no way to sift through all the data personally. So what's been done a lot is, machine learning has been implemented to find planets. People have come up with clever algorithms to do that. And that's what they've mostly been designed for, to find planets. And planets are basically our circular eclipsers, the golden standard. So the origins of these standard eclipses, as I would call them, is binary stars or brown dwarfs or planets. There are multiple algorithms that help you to model the object that's crossing, that's transiting the star. So you have, BLS, TLS is a newer one, Lone-Scargill, period folding. And the thing is, since you have a very large sample size, you can train machine learning quite effectively to find these things. So, there are a couple of things that are important. I'm simplifying, obviously, because it's a lot more complex, and I don't mean to oversimplify the work. But you basically have, the size of the star. You have limb darkening. That's another stellar parameter. You can have variability. So here you see, for example, a young star that has flares and sunspots and is rotating rapidly versus a very calm older star. Then you also have the size of the eclipser, obviously, because that's blocking the light. You have how quickly it's passing in front of the star. And you have an impact parameter because the size of the star changes depending on where it's crossing the star. So here are some examples. It's very clear that you can see something that's crossing in front. And I say easily recognizable, but of course, I know that a lot of work goes into sometimes finding these incredibly small signals in very noisy data, especially if you're looking from the ground. And one of the main features of these eclipses is that they are symmetric. And that's because we're looking at circular eclipsers. So the thing transiting the star is symmetric. So logically speaking, the eclipse would also be symmetric. Now, what happens when things start getting a little funky? So here are a couple of examples of eclipses that are very clearly not symmetric. In fact, you can see that for the first two, the ingress is significantly steeper than the egress, and for the last one, the opposite is true. Also, you can exceed this depth barrier of 50%. It's not necessarily a barrier, but one of the main things that happens is if you, for example, have a binary star system and one blocks the other, then more or less 50% of the light would be blocked. Unless you, of course, have a cooler star that is larger than a hotter, smaller one. So this is when we start getting into non-circular eclipses. So what is it exactly that I specifically am looking for? I'm looking for circumplanetary disks. And as soon as you start doing this, you start adding a whole bunch of parameters to the fitting. So first of all, you have your planet, but around that, you can have a circumplanetary disk. So you have the first obvious parameter is how large is the disk. The second is how inclined is the disk, because this introduces an asymmetry because now you're no longer looking at a circle, but at an ellipse. Furthermore, it can be tilted with respect to the orbital path. And of course, you have the final thing that the disk doesn't have to be 100% opaque. It can have a smaller opacity. Well, here, so the examples I showed above of the asymmetric eclipses, here are some models of the disks that crossed in front of the star to produce that particular eclipse. You can see that you have very inclined circumplanetary disks that have varying tilt angles and varying impact parameters. So the asymmetry rises in the end from a combination of the inclination, the tilt, and the impact parameter, which is clear if you, for example, look at the middle one, because that's the easiest to see. You can see that the angle at which the disk approaches the star is much different than the other side when it passes, when it leaves the star, basically, to put it that way. But we can go into much more complex eclipses because the ones I showed you before are quite simple. One of the golden standards is J1407 or V1400 Centauri. As you can see, it's a very complicated eclipse, and in the end, it has a 37-ring model to kind of match the different gradients that were measured in the 56-day eclipse. And below it, you see a new system that's still kind of in transit. It's been in transit now for over a year and it's still going. So, you know, these things are out there, and it could be very interesting to find out if we can model this as a ring system.
3 minutes.
Oh, thank you. So now we've included even more parameters to the space, because now instead of having a circumplanetary disk, we have something that can be split up into rings. So each ring has an inner radius, an outer radius, and opacity. And this makes it very hard because now intuitively there are too many parameters to just play around with, manually. So this is where Beyoncé comes in. So the idea is to explore a very large parameter space that's spanned by these ring systems. And it does that by splitting it up into two main modules, which I'll run through. So first there's the parameter explorer, which I call the shallot explorer. You'll see why soon. And a ring fitter. So the parameter explorer explores a 3D grid that is based on 3 coordinates. The first 2 are the X and Y coordinate of the anchor body. This is done in time space just to keep things easy. And a stretch factor in, just because I chose it, the Y direction. It might just as well have been the X direction. The process is quite fast because it's analytical. And the only actual input is the eclipse duration, which you can measure from the light curve. So this is basically how it works. You have a grid point, which is that XY coordinate of the center of the ellipse. And basically you try to find the smallest ellipse that touches the eclipse locations. So you have to think of this in time space, so that can sometimes be a little bit confusing, but this way you can determine the smallest ellipse that would cause an eclipse of that duration. And from that, you can determine the size, the inclination, and the tilt. Why is it called a shallot plot? Well, it's because of the plot that you see for the disk radius. And what we want to do is, what I showed you before only shows the smallest possible disks, but you can imagine that it can also be a much larger disk that, has a larger impact parameter. So we want to be able, that's why we have a third dimension that we explore. But now we just have a very large parameter space. We haven't done anything to limit it, so we're not helping ourselves at all. The way we can do that is basically through 2 separate things. We can measure the gradients, all the gradients that we see in the light curve, and we can use that to determine, to cut away at the parameter space. I'll skip through this. If you have questions, ask later. And of course you have the Hill radius because you have a maximum size that would be stable. And basically what we do is we assume that the ring system is azimuthically symmetric. It's made of concentric rings, and that we make the assumption that the steepest gradient is due to a fully opaque ring transiting the star. So the ring doesn't necessarily have to be that opaque, so the gradients could be smaller. So this gives us an upper bound. So basically here you see some examples. You see on the upper panels, you see the full parameter space, and on the lower panels, you see that it's been rounded off because of the Hill sphere, and it's been cut away at the sides because of the gradients that were measured in the light curve. So, okay, there are some limitations to this. This is basically done on the assumption that the disk is much larger than the star, because things get complicated once they're similar sizes, because the duration of the transit is no longer dependent just on the size of the disk. But let's move then on to the second part, which is the ring fitter. Basically, once you have used the shallot explorer, you have a geometry for the system, and now you want to actually fit the light curve. So you have all these parameters as shown here, and you fix that, and then you basically go through this algorithm, which I'm going to show an example of quickly. So basically, it starts with you have a single disk, then you optimize the opacity, then you split it in, for example, 2, but you could have split it in 3. You optimize the opacities again, and you keep doing this until you've reached a number that you're satisfied. Then, oh, sorry, I skipped too fast. Then what you can do at a certain point is you can merge rings that have very similar opacities. Because of course, if you have a ring that's at 0.1 opacity and one that's at 0.1005, you want to have a solution with the least number of rings, and you don't want to overfit for the noise. So you start merging rings, and then you optimize again. And then a final thing is that because you're dividing the rings evenly, you have fixed boundaries for the rings. So you want those to be able to shift. So at a certain point, when you've done the merging and you've finished optimizing, you can run it through an MC fitter to be able to shift the ring boundaries a bit. So basically, that's what this is. What Beyonce is going to be capable of in the future. Currently, I'm testing it on simulated light curves, and I'll be trying to reproduce or improve on the model of J1407. I'll also be, if it's successful, I'll use it also on the new J0600 that I showed before, the year-long eclipse. And I'm going to be keeping on working on this, and I'll be posting, I have a poster for the ES meeting in 2021, and there'll be updates there. So if there are any questions, please feel free to ask.
Great, thank you very much for the very nice talk. So we have some time for questions. So yeah, and now we have a question from Harish. Do you want to unmute and ask the question?
Yeah, my question is about the complexity in the model, because there are a lot of free parameters. And when you showed some examples of non-symmetric eclipses, it looked like the light curves could be described by less number of parameters. And so like at what point would you know that you put too much complexity in the model, in that you're not getting a unique disk solution?
Well, so for, let me scroll back up to. So for models like these are quite simple. So you wouldn't necessarily need to run through Beyonce to do this. The problem as well that you can see if I show the models that were at, is that you can see that the disk size is comparable to the star. So I need to check the bounds of when this is useful, because at a certain point also the parameter explorer would break down because of the the comparable sizes. And then you'd probably be better off using another software. But once you start getting into eclipses that look like this, then you need those extra parameters, because there's no other way to do this.
Yeah, of course. Yeah, this one is really complicated. So you can
yeah. But no, for simple ones like this, it would be of limited use. But the thing is, right now, so I've only shown 2 examples here, but I'm currently working on a separate one that's popping up, and the surveys are getting better at flagging these kind of weird things, whereas before it was kind of like, junk, something's off. Now people get flagged like, hey, maybe this is somebody's treasure,
Great, thank you. So we also have a question from Paul. Do you want to unmute and ask?
Yes, I was wondering, is there any way that you can actually deal with noise from stellar variability with this?
Well, ideally you would clean the light curve from stellar variability before that, because
ideally.
Ideally, yeah. I mean, you'd have to clean it. Sometimes, of course, you'd have to catch flares or stuff like that, but that would be part of the. Well, yeah, you'd have to do that beforehand.
There's no kind of diagnostic you can pull out of fitting parameters that, because you have a certain symmetry in the system, and that variability is a time parameter, so you might be able to do something with that.
Well, see, one of the major problems, I'm not sure if I'm properly answering the question, but one of the major problems that we have with systems like these is that they're mainly single transit. So we don't have, we can't period fold and then see anything that's, that doesn't repeat or is out of phase, that could be because of stellar variability. So basically we would look at all the out of eclipse data and then try to get the stellar variability from that.
No, I meant your geometry has a symmetry in it.
Yeah.
Well, it will be interesting to see how it actually does the fitting.
Well, look forward to it at ES if you're joining.
Great, thank you very much for the nice talk. So I think we're at the end of the time here. And again, thanks to all the speakers today. It was a very great session. And for the next for the next NOVA Network 2 meeting, I think we will get in touch with you. It will be probably in a few months' time. So are there any questions, comments? So I just also want to emphasize that please keep the discussion going in the Slack channel. So, and the speakers, please, if you can, monitor the Slack. So if there are any questions, so you can answer them there. So any questions, comments? Cool, so I don't see anything, and I guess thank you everybody, and yeah, hopefully, yeah, so I think the next meeting will be tomorrow, so yeah, great.
Good. Okay, thank you very much.